Okay, that's fine.
Yeah.
Okay, we shall start now. So probably it's due to the early time and the workshop room is too difficult to find. So we do have a lot of participants here. But welcome to the second workshop of our series called Mobile Intelligent Photography and Imaging, MIPI workshop. So on behalf of the organizing committee, we welcome your attendance. And the workshop organizers are led by Dr. Lee Chongyi. And first, we welcome you to the workshop. So we had our last workshop back in ECCV 2022 last year, and this is the second one. The objective is to encourage research and discussion in new sensors and imaging system. So we have organized 4 challenge tracks. So I will introduce the tracks later. Out of which we have released almost 27,000 pairs of data in the challenge. And we received 27 submissions altogether. I will announce the winners later. And we have received quite some number of papers, and we accepted 5 of them. We have invited 4 distinguished speakers in this workshop, and this workshop has led to an IJCV special issue, of which the deadline is 1st of August. So far, we have already received 20 submissions. So this is the lineup of our keynote speakers. The first speaker will be Dr. Liu Jiaying. So she will connect through Zoom and deliver the talk online. But the rest of the speakers will come to our workshop and deliver their keynote. So these are the tracks of our challenge. We have RGB plus TOF depth completion, and RGB W joint mosaic denoise, joint fusion denoise, and nighttime flare removal. And here are the winners of each of the track. So I won't go through the list, but you can find the winning solution and the introduction of the data set on our technical report, which have been released on arXiv. And congratulations to the winners. So this is the call for papers for our IJCV special issue on mobile intelligent photography and imaging. And the submission deadline is 1st of August. So if you're interested and if you have any good papers, please submit to this special issue. So this is the schedule today. After the opening remark, then we will have Professor Liu Jiaying to deliver her keynote. And after that, Professor Felix, Professor Xue, and Professor Sabine Sastre will deliver a speech. So it's a half-day event. We will end noontime. So without further ado, let's invite Professor Liu to deliver a keynote. So before we start, just a little bit of introduction of Professor Liu. So Professor Liu is an associate professor in Peking University, China. She has authored more than 100 technical articles in referee journals and proceedings and holds 70 granted patents. Her current research interests include intelligent multimedia computing and computer vision. She has served as the associate editor of TIP, TCSVT. So she's also the ASPA Distinguished Lecturer. So Professor Liu, over to you. I will unshare my screen.
So could you hear me?
Yep.
Okay, so let me share my screen. So could you see my screen?
Yep, it's good.
Okay, cool. Thank you for the introduction and inviting me to give a talk. And I'm very sorry because the visa issue, so I couldn't go there. So I probably like to try to share my talk and with this online. And today's talk is titled with low light image enhancement for the intelligent analytics. So in this talk, I will try to inspire the thinking how to bridge the light enhancement and low-level vision problems and boosting the high-level vision algorithm in the dark condition. So we all face those kind of problems when we take pictures in the low light conditions, especially with the cell phone. So the overall brightness and the contrast are usually very low. So it results in the very poor visibility and the blurry details. So due to the insufficient light entering the sensors and output of the photosensitive the elements is quite low. So it makes the internal noise of the image system more apparent and leading to the significant amount of noise. So once we enhance the low light images by simple operations like the histogram equalization, so the noise becomes very visible. So upon closer inspection, so we can observe that although the simple processing techniques are capable of enhancing the brightness, also significantly amplify the noise represented in the image. So existing the low light image enhancement algorithm offers those kind of problems. So moreover, low light images often suffer from the uneven illumination. So that is the overexposed or the underexposed regions after the brightness enhancement. So another issue is also very we need to consider in the low light scenario. That is the failure of the high level vision algorithm at low light condition. So the low light not only affects the human vision, but also poses the challenges for the machine vision. So such as the nighttime autonomous driving and the civilian video analysis. So on the right side are the face detection results under the normal lighting, while on the left side are the face detection results under the low light condition. So the middle column visualizes the corresponding images enhanced using LIME algorithm. So it can observe that the detection performance is well trained on the normal lighting, but it gets worse significantly at low light conditions. So first, let us briefly review the previous related works. The simplest and the most intuitive method is to directly enhance the brightness of the low light image. However, this operation can cause other issues such as over saturation and the loss of details in the brightness regions. So the methods based on the histogram equalization aim to flatten the histogram of an image and expand the dynamic range of the brightness to address the above issues. However, the results of these methods often suffer from the inadequate or the excessive brightness enhancement, as well as the significant noise. So some researchers have noticed that the invert low light images similar with the haze images. So based on this observation, they have attempted to apply well-established dehazing methods on the inverted images. Then the dehazed image is inverted again to obtain the final result. So to address the issue of noise, these methods often require an additional noise denoising step. So the methods based on the Retinex theory perceive the scene observed by the human eye as the product of the reflectance layer and illumination layer. So by boosting and enhancing the illumination layer, the original image can be enhanced. So deep learning-based methods are built upon the dataset that include a large number of the paired low light and normal light images. The regression model can be utilized to map the low light image to their corresponding normal light counterparts. So Laura proposed a deep autoencoder that performs contrast enhancement and denoising simultaneously and sequentially. So the model is designed to effectively enhance the contrast of the low light images while reducing the noise artifacts. So in BMVC 2018, we tried to combine the superior of the data-driven methods and the RetineX-based methods. It's a little trial to use the regression and to illuminate the adjustment. So we try to learn the mapping between the low light and normal light images in the well-designed signal domain, the RetineX domain. So we first collect a paired low light and normal light natural images dataset. And we designed a deep network to decompose the low light images and adjust the illumination adaptively in a data-driven way. So our RetineX net can be divided into 3 steps: decomposition, adjustment, and recomposition. So in the first decomposition step, a subnetwork DecomNet decomposes the input image into the reflectance and the illumination. So in the adjustment step, an encoder-decoder-based network brights up the illumination, and the noises on the reflectance are also removed at this step. So finally, we reconstruct the adjust illumination and the reflectance to get the enhanced result. So to facilitate the training of our network, we construct a large paired dataset consisting of the 1,000 images in low light and normal light conditions. So the dataset is divided into 2 parts, the real capture images and the synthesis images. So first, we collect the 500 pairs of the real images and representing low light and normal light conditions. So these pairs are obtained by adjusting exposure time and ISO parameters to control the lighting conditions. We also utilize the raw pictures to synthesize some images. So we adjust the brightness of the raw image and make the wide channel histogram of those as close as the real one. So it can be observed that the results obtained from the manually designed decomposition method are not consistent for the reflectance layer. And sometimes it cannot effectively handle the color of the image, resulting in the black shadows in the reflectance layer. But for our RetineX net can preserve the consistency in the reflectance layer and the smoothness in the illumination layer and the structure relevance. So this comparison demonstrates the brightness enhancement results on a real-world dataset. So our method products more natural and harmonious color as well as cleaner details. So in the recent years, more works have focused on the joint enhancement and understanding problems. So there are many datasets that are currently available for evaluating the high-level vision tasks under the low light conditions. So for example, the CAST dataset is widely used for the pedestrian detection in low light environments. So it contains RGB and infra images captured in the various traffic scenes during both the daytime and nighttime. So exclusive dark dataset is a dataset for the object detection in the low light conditions. It focuses on the nighttime scenes and contains the images with 10 different levels of the nighttime illumination. And the dataset covers various object categories and provides annotated bounding box for the 12 different classes of the objects. So to promote and inspire further research on the data-driven methods, several low-light data sets involving both the high-level and the low-level visual content have been proposed. So based on those kind of works, in 2021, we wrote a survey paper at IGCV, trying to provide a benchmark for comprehensive low-light image enhancement methods as well. So this is a timeline illustrating the development of the various low-light enhancement methods. So in the 2017, deep learning methods engaged as a significant milestone, subsequently becoming the mainstream approach for the low-light enhancement. So in this paper, we have provided a comprehensive summary of low-light methods. So if you are interested, please refer to the original paper for further exploration. So in addition to comprehensive survey, we also introduced a large-scale dataset that offers several advantages compared to the previous related works. So for this dataset, it has a full purpose. So the dataset can be utilized for both low-level vision tasks and high-level vision evaluation tasks. So for the second advantage, it's reality. So it contains a real captured paired low and normal light images and ensuring the realism of the dataset. So the third one is a diversity. So the VLOLL comprises synthesis images with a diverse backgrounds and objects. And finally is large scale. So VLOLH contains a subsequential number of the images like the 10,000 compared to the size of the wider phase dataset captured under the normal lighting conditions. So such a large scale dataset facilitates robustness for the model training. So this is a comparison to other detection-related datasets. So exclusive dark is a dataset specifically designed for object detection and cannot be used for the evaluating face detection performance. And the remaining datasets do not contain the sufficient number of the low-light scenarios required for the comprehensive evaluation. So here are some examples of the actual shooting pictures from the dataset. So the leftmost column represents images captured under the normal lighting conditions, while the next three columns depict the corresponding images captured under the low light conditions. So here are some examples of the synthesis image from the dataset. So these images are created to augment the dataset and provide the additionally diversity in terms of the background and the objects. Here are some examples of the images with the face detection in the this dataset. So the image in the first and the third column represent the low light images, while the images in the second and the fourth columns shows the corresponding images after being enhanced using the line method. And the ground truth face in the images are highlighted with the green bounding boxes. So here are some example of the existing face detection model, DSFD. The predicted face in the images are highlighted with the green bounding boxes. Here are more examples of the face detection images in the dataset. So the first column on the left shows the images captured in the low light conditions, while the second and the third and the fourth columns display the corresponding images enhanced using the LAM, MSR, and MF methods respectively. So for our face detection dataset has a very diverse faces of the varying resolutions, poses, levels of the occlusion, and the lighting conditions. We have also made some statistic of this data set. So from left to right, it shows the statistic of the face resolution in the training and the testing set. Here are the numbers of the faces in the training and the testing set. Based on the proposed data set, we conduct a large number of evaluation. We employ various quality assessment metrics, including the reference-based, reference-free, and the perception-based metrics. So the results are represented by the red, blue, and orange, indicates the best and the second best and the third best results in each row, respectively. And here are the results on the synthesis images. Here are the results on the real images. Additionally, we have compared the running time of the different methods to assess their efficiency. Here is a set of images that are enhanced by using different methods. We also tested the left figure shows the PR curve of the various face detection methods, the DSFD, pyramid box, SRN, SSH, and the fast RCNN on the original dataset. So on the right side, we present our PR curve of the DSFD on the dataset after applying different illumination enhancement methods to the images. We also show the combination of the pyramid box and SRN with various low-light enhancement methods. So this set of the image displays the testing results of a different face detection methods, DFSD, pyramid box, SSH, and the fast RCNN on the three subsets of the test set, which are divided based on the different face resolutions. So intuitively, the results show that the small faces are generally more difficult. And this is the detection performance categorized by the face illumination. As we can see, the darker faces are more challenged. So in this work, we also discussed try to address the joint issue of the visual enhancement and the downstream face detection. So the low-light enhancement model typically consists of the encoder and the decoder. So the encoder extracts the feature while the decoder maps these features back to the reconstructed images. But for the detection model, it goes through three steps: the feature extraction, the feature fusion, and the bounding box prediction. So to achieve better integration of the enhancement and the detection, we mainly focus on the challenge of the obtain the paired images with bounding box in the real world scenarios and making efforts in the exploring the following two aspects. The first idea is to, during the enhancement stage, we take into account both paired and unpaired data and employ a cyclic prior model in the detection phase. We input both the low-light image and the enhancement image and fuse them features at a later stage. And the bounding box prediction is performed based on their fused features. So the second is we aim to obtain the more interactive and the correspondence between the features of the enhancement network and the detection network, so the benefiting both the enhancement and the detection tasks. So in detail, we propose a method that addresses both the illumination enhancement and the detection tasks at the same time. So first, we employ a half a cyclic constraint to perform the illumination enhancement. So the model is trained with the paired low light and normal light images, as well as the face images captured under the low light conditions. By doing so, the model learns to restore the illumination conditions and capture the feature beneficial for the face detection. Then we utilize a multiple path fusion network to aggregate information from different lighting environments And this network allows us to effectively incorporate the features from the various illumination conditions, enhancing the overall detection's performance. So we employ the term L enhance and L consistency to constrain the illumination enhancement. And the gamma represents the weighting parameter that the trade-off between the loss using the real and the synthesis images. And the multiple pass fusion network module aggregates features learned under different lighting conditions and feeding them into the subsequent bounding box regression network. This fusion process enables the model to leverage the information from the diverse lighting environment for the improved detection accuracy. So we have designed the fishnet to better utilize the information from different skills and promote the interaction and the collaboration between the features extraction during the enhancement and the detection stages. This is a performance demonstration of our method on the dataset. So the multiple detection loss represents the constraint applied to two branches using separate bounding box regression networks. It can be observed that our method outperforms the results obtained by directly training on the enhancement images. So the last two rows of the comparison highlights the effectiveness of the multiple detection loss. So then at CVPR 2021, we propose a joint high-low adaptation method for the low light phase detection. We try to further investigate this joint high-low processing CV problem. So well, one straightforward method to address those kind of issues is to conduct a dedicated dataset, specifically for the low light phase detection. But this process is a time-consuming and resource-intensive. Moreover, it overlooks the existing datasets available for the normal light phase detection. So therefore, our research aims to explore methods for reducing the human supervision in low light phase detection tasks. So in this work, we explore the following problems, giving the labeled data for the normal light phase detection and unlabeled data for the low light phase detection. How can we transfer the model from the normal light conditions to low light condition? So if successful, this method eliminates this need to annotate the bounding box for the low light phase detection. So by collecting nighttime images, we can accomplish the low light phase detection and significantly reduce the human efforts and the resources required for the data annotation. So the challenges of the adapting model from the normal light to the low light lies in that the gap is very huge and complex. And the two different domains not only have a different pixel level appearances, such as the illumination, noise pattern, and the color casts, but also contain the different objects and the things, such as the street lights, vehicle headlights, and advertisement boards. So in other words, they are both high-level and low-level gaps. So to address the difference between the low light and normal light images, we propose a joint low-level and high-level adaptation approach. So in the result images, it can be observed that in comparison to the LAM plus DSFD method, our method achieves accurate phase detection and remains unaffected by the objects, such as the street lights. So before introducing our method, let's briefly review the existing adapting low light detection techniques. So enhancement-based methods always brighten the low light images and directly testing on them. They usually require no model refine tune, and therefore they are very highly flexible. And the darkening-based methods first darken the normal light data into a dark version, and then retrain the model on the transferred annotated data. And the feature adaptation methods directly adapt the feature of the face detection model. So although these methods can narrow the gap to some extent, so the enhancement and the darkening based methods only consider the pixel level gap. And the feature adaptation methods instead try to fill the whole gap in the one step. So these performances are usually not very unsatisfactory. So we instead consider joint the low level and high level adaptation. So for the domain, the low light L and the normal light H, we first narrow the low level gap. Different from the enhancement of the darkening based methods, we set up an intermediate state to make the two domains take a step towards each other. So low light degradation is a very complex process, and we roughly decompose the related factor into three aspects: illumination, noise, and the color bias. Although denoising and the color correction is difficult, but adding noise and applying the color bias inversely is relatively easy. So we bright L into EL and distort H with the noises and the color bias to form the DH. Then we push the EL, H, and the DH towards each other on the feature level. We also enhance the representation on this domain. So our more detailed framework is shown on this slide. So process for the low-level adaptation are colored blue, and the process for the high-level adaptation are colored green. And for low-level adaptation, we use an enhancement network for the brightening, the illumination, and we use nonlinear curve mapping and increase the iterative number and the width of network to improve the performance. We also designed the learning-based strategy for the noise synthesis and finally apply the color jittering. Here are the visualization for the pixel level transferring. Compared with the other image translation methods, our method can better narrow the pixel level distance of the two domains. For the high-level adaptation, we use a combination of the three tasks. Unlike the previous unsupervised domain adaptation approaches, we have discovered that using the self-supervised learning tasks for the feature adaptation provides better stability and performance. We designed the three tasks. First, the middle task aimed to bring EL and H closer together, and we have employed a jigsaw puzzle-based self-supervised learning task for this purpose. And simultaneously, the task at the bottom involved the contrastive learning, self-supervised learning on the EL, H, and the DH. To bring the H and the DH closer, we treat DH as the positive samples for the corresponding images in H. And finally, we have conducted separate contrastive learning, self-supervised learning on the EL to enhance its feature representation. Experiments are based on the dark face dataset. So first, we conduct a benchmark on existing methods, applying model trained on the darker face datasets with the normal lighting conditions to the dark face dataset, yield the suboptimal results, and the best performance method achieves only the 16.1% MAP. So for combining a low light enhancement methods with a face detection model, the best approach achieved a MAP only the 41.4 when using the combination of the MF and the DSFD. But in the left table, we also attempt to use the unsupervised image-to-image translation method, such as the cycle gain, to darken the wider face dataset and then training on the darkened images. However, the results were not very good. And in the red table, we explore the traditional unsupervised domain adaptation methods. Among them, the pseudo-label approaches the best performance, but it still only reached a MAP of the 35.1%. So to compare the various methods, our approach achieved a remarkable MAP of the 44.4, surpassing other technicals by the significant margin. So furthermore, when compared to the upper bound represented by the labeled training, we are able to narrow the gap to a mere 1.6% in the terms of the MAP. So there are subjective results comparing our method with the enhanced technicals. So as we can see, we correctly identify more faces and did not mistakenly identify the windows as the faces. Our framework is not only for the supervised, unsupervised model adaptation, but also for the supervised learning. For instance, on the dark face dataset, the supervised learning performance increased from the 0.460 to the 0.486 through our approach. So furthermore, our framework can also be utilized to the transfer object detection models from the COCO dataset to the exclusive dark dataset. So we studied the illumination enhancement method for the unsupervised adaptation at ACM Multimedia last year. We tried to learn the self-aligned concave curve to improve both the visual adjustment and downstream tasks performance. So existing work can be classified into two categories: low-light image enhancement methods that only focus on the image restoration, and the domain adaptation methods, including our previous work, HLA phase, has only considered the downstream CV tasks. So however, we have discovered that current domain adaptation methods has a superior vision tasks, but neglecting the importance of the illumination adjustment. So they fail to fully exploit the potential of the illumination adjustment in enhancing the performance of the downstream vision tasks. So therefore, we have embarked on exploring of how to perform domain adaptation from normal light to the low light conditions using the illumination enhancement technicals exclusively. The challenge lies in how to find a way to restore underexposed images or videos from the perspective of the machine vision. To achieve this goal, we propose the framework consists of the two aspects: network design and the training strategy. So for the network design, we propose an architecture that can maximize the model scalability and to be easily to learn. And through training strategy, we design how to adjust the illumination from the perspective of the machine vision. So next, I will introduce the technical detail of our method. So idea of our method is to find a function G, to use it to enhance the low light input. So we'll assume that G should follow the four constraints. So the first two, G should be past the 0, 0 and the 1, 1, and increase the monotonically. And the third, the G should be spatially shared, and we propose to ignore spatial variance, such as the lens fall off and the signal dependent noise. And then we assume G to be the same for each pixel in an image. Fourth, inspired by the camera response functions, we assume that G should be concave. As shown in the figures, most real camera response functions are the concave. It is because the human perception of the brightness is more sensitive to the differences in the darkened tone than in the lighter tones. So accordingly, enhancing illumination is a concave transformation. In summary, G should be a concave curve, and the next question is how to design the neural network that meets these constraints. So we propose a network called the deep concave curve. We use the neural network C to predict features from the input low-light images. So instead of directly estimating the G, the network C predicts the minus second derivative By setting the last layer of the network C to the ReLU, we ensure that it is non-negative. Then we integrate the second derivative and normalize it to fit the range of the 0, 1. And the discrete integer is implemented as a matrix factor multiplication. So since the second derivative is a non-negative, we can guarantee that G is monotonically increasingly and concave. So the first constraint is satisfied by the normalization, and the second and the fourth constraint are satisfied by the discrete integer. And for the third constraint, we let G be a mapping from original pixel values to a new pixel values. It is also equal to a lookup table. We also predict an independent G for each color channel. It can increase the flexible on the model. For the training strategy, we propose a symmetric self-supervised alignment. So our idea is to employ the high-level vision models as guidance, existing strategy using the disparity matrix and adversary learning. But they bring the extra semantic supervision, which can mislead our model and making the training hard to converge. So we're instead using the cross-domain self-supervised pretext tasks. So this is our training framework. So giving a pre-trained and fixed weight feature extractor. We first train the pretext head on a normal light images. Then we train our model with the fixed weight head on the low light images. We use the rotate jigsaw puzzles as the pretext task. We first rotate the input images by the random angles. Then we apply the 3x3 jigsaw shuffling and asking the network to recognize the permutation. So with the above designs, we propose a new unsupervised low-light adaptation framework. It's named as a self-aligned concave curve, or the SACC in short. Given a pre-trained normal light downstream model, we use its feature backbone to train our deep concave curve. While the testing, we first enhance the input image and then apply the downstream model. So different from the existing method, our model is blind to both normal and low light annotations. So furthermore, our model does not even need to adjust the downstream model. Here are some discussion. So besides insufficient light, there are other low light factors such as the color bias and noise. But for the color bias, our model is able to handle the color bias because our model has independent curve for each color channel. And for noise, we notice that although the real camera noise is quite hard to remove, improving the model's robustness to noise is much easier. So we adopt the pseudo label to adapt the downstream model, and this advanced version is called the SACC+. We also have an in-depth analysis of our technical design. First, we discuss the possibility of replacing the rotated jigsaw with other learning strategy. We try the discrepancy matrix and adversary learning and other self-supervised learning methods, but the performance will drop, which can demonstrate our methods. We also discuss under the proposed training strategy whether our deep concave curve is better than other network architecture. We explore the two representative the SALTAM model in light gain and zero DCE. As shown in the figure, we generate weird line artifacts. These lines are trivial solutions for the rotated jigsaw permutation problem. But in other words, in light gun and the zero DCE get the overfitted to the rotate jigsaw task. So thus they cannot generalize to the downstream high-level vision tasks. We further explore the necessity of each constraint. Too weak or the too strong constraints both lead to worse results. The concave constraint, while the first derivative is greater than 0 and the second derivative is less than 0, has the best performance. We also discussed the combination of our training strategy with inline gain and zero DCE. The above experiments show that our network and the training strategy work best together. So finally, we also discussed the necessity of the denoising. We tested two representative the denoising methods, BM3D and the neighbor to neighbor. Here we can see these denoising methods degrade the performance. It may be because the denoising also blurs details, which will affect the machine vision. So in comparison, our advanced version SACC Plus has the best result. So for the experiments, we test our model on the five settings. We first evaluate our approaches by one of the most fundamental vision tasks, image classification. So for the table, we can see that our SACC best adapts the daytime classifier to the nighttime. And with the help of the pseudo-label fine-tuning, the accuracy of our SACC Plus is even higher. And for another task, the unsupervised dark phase detection, our methods also beat the state-of-the-art methods. Here are some subjective results. We can see that our model detects the phase more correctly. Although initially designed for the images for our algorithm, but our methods can also generalize into the video tasks. Here we show that our model can improve the low-light video action recognition. We also explore the task that differs a lot from the classification and detection, which is optical flow estimation. Here are some of the take-home message for my whole talk. So in my talk, I introduce our work in the low-light image enhancement for the intelligent analytics. So the low light suffer from the low visibility, low contrast, and intensive noise. It poses challenges for the visual unpleasure, which corresponds to the human vision, and the system failure, which corresponds to the machine vision. So for human vision, we consider robustness enhancement, and I introduce our work for the expanding structure deep prior to the deep Retina-X and our benchmarking and data set. And for the machine vision, we solve the joint enhancement and the downstream computer vision tasks. We consider the joint high-level and the low-level adaptation and design the self-aligned the concave curve. So that's the end of my talk, and thank you for your attention. Any question?
Right. Thank you, Jiaying. Okay, so any questions from the floor? We still have a few minutes for the questions before the next talk by Felix. Yeah, please use the mic.
Hi there. I am curious on the deep concave curve. What happens if you try to apply that after some tone mapping has been adapted, used to the image? Because if you do that after tone mapping is going to be concave. Usually it's going to be an S-shaped curve. So have you tried to do it only in raw, or have you tried to do that both in raw and after tone mapping of the images?
I think the microphone is not very clear. Could you help me to repeat, Kevin?
Maybe you can use this mic instead. Yeah, because it's closer to the computer. Okay.
Sorry for
no. So my question, sorry, my question is that so the deep concave curve. So I fully agree. You know, if you have a raw image, the first thing you do is just having some camera response function that it's usually concave. But as you go further on the image pipeline, you go with through tone mapping, and tone mapping is no longer concave. So have you tried that? What happens with the deep concave curve, both at raw level and when you already have gone after tone mapping? Is there any difference, or is there any problem you may notice?
So I think you're asking the mapping problem, right? For if we change the downstream task, but we still need to align the normal light and the low light.
Maybe let me reshape
Yeah,
the question a bit. So it's about the deep concave modeling. So is there any difference applied it before and after the tone mapping? Because tone mapping is not concave.
Okay.
Yeah.
Yeah, I think we just assume this concave curve can help to do the enhancement, but if you testing the tone mapping part, but I think it maybe get another solution for those kind of the lighting parts. Yeah.
Okay. Thank you. Yeah, I can use this. Thank you. Yeah, another question for you.
Thank you for the talk and the good talk. So I have one quick question regarding your benchmark and the time for the your data set. Just wondering, just for the from mobile platform or from the PC? I think the slide that your data set the benchmarking.
You mean the
your data set benchmark the low light enhanced result? I just
Okay.
wondering the time measurement is from the mobile platform or not.
Oh, it's for PC. We during that time for that's the survey paper. We do not to test for the mobile, but we try to compare at for the PC time. Yeah.
Oh, okay.
I think you just mentioned because we want to make the reference for the different time consuming the method, so we just to calculate the time. Yeah.
Oh, okay. Thank you. Second question is a quick question, because there is low light enhancement, right? Usually the color get enhanced actually introduce a lot of chroma noise. So do you have some metric to measure the chroma noise after enhancement compared to ground truth?
I think that's why we want to test on the high level vision task, because it's more be accuracy to describe all the performance. And but for the Chrome, I think currently we usually to do like the also for like the subjective measurements or some like the PSNR part. Yeah, but sometimes it's for the color bells, they're not very consistent metrics to judge the Chrome part, I think.
Oh, okay. All right. Okay. Thank you. Yeah.
Thank you. Pei-Fan, yeah.
That's a very good question.
Thank you. Very nice presentation. I just have one short question. So when you try to synthesize this kind of a low light, like trying to use the normal lighting condition image to synthesize low light, you add some noise. Do you use just a simple Gaussian Poisson noise, but do you consider even more fancy noise model, like say dark current or like a row pattern noise? Or this is really like hard to model noise modeling? And the follow-up questions that if you're using the simple noise model, do you think actually even the models trained on those simple models can generalize to more challenging cases? Thank you.
Yeah, I think for the darkening part, the noise is definitely not follow the Gaussian noise, right? So people, I think for the signal processing guys, they want to modeling very complicated denoising part. But for our part, I think we usually, like in our the last work, we try to directly use a pseudo label to do the denoising part. It looks well, and but I think if we can use some very complicated denoising modeling, and we definitely got the very well result. But I'm not sure for the joint high-low task. It is maybe not very, how to say, it's very effectively, because for some of the high level vision tasks, the noise may be a little bit effect, but I'm not sure if we try to made it very clean, it will get very high accuracy. Yeah.
Thank you. I mean, that's also kind of my impression. People have a very fancy noise pattern, but actually sometimes I'm not sure that's in practice actually really need that. So that's why I'm also asking. And thanks for sharing your thoughts on that.
Yeah, so I think maybe for the subject, if you want to both the visual pleasing and the high level task, the performance, maybe we can try more complicated denoising model. But if we only consider for the machine vision, I think if we get very robust feature, accepting the noisy affecting, so I'm not sure it maybe it not very affect a lot. Yeah, I'll agree with you. Thank you.
Yeah, that makes sense. Thanks.
Thank you, Tenfan, for the question. So, Jiaying, we actually have a nice gift for you. But
thank you.
You are not here, so we deliver to you when we go back to China.
Sure,
Yeah.
sure.
Okay,
Thank
okay.
you. Yeah.
Thank you. So we're going to have 3 more talks later by Felix, Professor Sabine, and Tenfan. So without further ado, I would like to invite Felix for the next talk. But before that, we need to introduce you. Okay. So 1 second. Okay, I'll pass the host to Chongyi. Yeah.
Thank you, Kevin. It's my honor to host this workshop with Prof. Kevin. Our next keynote speaker is Felix Hitt. Felix Hitt is a professor at Princeton University and co-founder and chief technology officer of self-driving vehicle staff Algolax. He is researching the theory and application of computational imaging and communication systems, exploring imaging, vision, and display system end-to-end. Felix's work lies at the intersection of optics, machine learning, optimizing, and computer graphics and computer vision. Now, I will hand over the stage to Felix. Your laptop.
Yeah, exactly. I use HDMI.
If you save one, because it's recording.
Oh,
Do you have the flash disk?
I don't think this will work
Okay.
easily.
So, okay. So you can just use your.
Thank you very much for the kind introduction. So let's see this video plays here. Computer scientists have created the world's smallest camera. It is the size of a grain of salt. Even crazier, it takes a photo and then spits out a very tiny photo. Just like, as you can see, nobody move, nobody breathe. That's $200,000. All right, so just want to start with this little clip here and present actually some of these cameras that guy here is talking about. Well, the key idea behind these cameras are covered here with this based on the line of capture, this line of projects that we did last year and the year before, is to design cameras as differentiable operators, so similar to neural networks. So can we design cameras or blocks of the camera itself in a differentiable fashion? So taking a step back, cameras are all around us in a wide variety of applications, from photography all the way to robotics, microscopy, health, and obviously in automotive and scientific applications. And in each of these applications, we use specialized compound optics. Now, this talk is not only going to be about optics, but that's one of the key pieces and one of the exciting pieces that I think if we can make that differentiable, that opens up a lot of interesting areas. So let's take a look at how the capture pipeline works. So taking even a step back further. So light from the scene enters our camera, and there it gets focused, hopefully, by a compound optic, which is conventionally a set of different optical elements all stacked on top of each other to record an image. That image is then processed by an ISP pipeline. The raw image is processed into a nice JPEG that is consumed then by a deeper network to, for example, predict objects in that scene, or do some other image-to-image processing. Now, we as researchers have come up with ways to very efficiently train these downstream computer vision networks. So those blocks are differentiable, and also been able to make a lot of low-level image processing differentiable, and seeing amazing results in this workshop here that show us the benefits of that. Now, all of the stuff before, though, was not really differentiable, or hasn't really been differentiable. There have been individual applications where folks have made individual blocks slightly differentiable with their individual metrics, but haven't really seen combined stacks. So largely, the industry, at least, does design these blocks in isolation. So I want to look at an approach how we can make them differentiable. I want to start with compound optics. So here we rely on modeling spatially varying point spread functions, or PSFs, as a model of the aberrations of the optics. And the shape of these PSFs basically describe what the optics do, depend on the lens profile, so lens radius, the conic constants, lens coefficients of the specific surface profiles that we have, the spacing in between the different lenses, and the glass material, and so on, or a compound optic. So how do we make such a block differentiable? Well, we have really good simulators, such as Emacs or Code 5, so we can actually forward simulate the entire optical model and use a ray tracer that does that really effectively. So we can get PSFs out and vignetting constants in order to describe our optical model. Now, one trick that we came up with is, well, we can actually learn potentially a proxy model that approximates in a differentiable fashion what Emacs does. So we're coming up with this network that predicts here a PSF and a vignetting factor. So our network is composed of two components here. A first stage MLP that predicts this low dimensional feature map and vignetting factor. And then we have a convolutional decoder that gets us a nice PSF with convolutions over the spatial space and output, and is trainable in the network fashion. So we train this then by sampling with different parameters or Emacs model, that we get different PSFs, and we can use that as supervised training data to train our model with these two losses that I'm showing. And then we fix this, and we have a differentiable model. And as long as you sample the parameter space good enough, you can actually then train your compound lens with this proxy function. And so here you see the optimization and process. And the task loss here decreases. So what's the task loss? Well, we can actually now optimize our model by combining it together with the downstream loss, with the downstream network. So this is pretty exciting, because we can, for example, combine it with a downstream detector and directly optimize for an IOU loss, which is what we did here. So here's a downstream downstream optimized lens. And what you see here is that the lens that we get here has a lower F number, so it actually produces images with less noise at the cost of some off-axis aberrations, which we can live with in this model. So something that a traditional optics designer would not come up with. Here's some examples. For example, this person and bike are correctly identified in this case here. All right, so I've shown you one example how we can make compound optics differentiable. Now, can we go one step further and design these ultra small optics that I mentioned at the very beginning of my talk that can potentially completely replace compound optics? So can we get rid of this entire stack of the compound optics and replace it with a single surface here that's ultra flat? We use meta surfaces to do that. So meta surfaces are an array of sub-wavelength nano antennas that allow us to modulate light with much finer control than conventional optics that bend and steer light at these glass to air surfaces. And the idea is that we can use computational imaging, so jointly design an optic in a differentiable fashion with computation in the backend. So we use these meta surfaces. Here's an example of this tiny meta surface that we built as non-glass materials that can hopefully provide the same optical focusing power as conventional lenses. And again, we hinge on this idea that we want to design this thing with a differentiable operator. So we want to come up with a model that brings a meta surface design, which traditionally is designed in relatively costly Fourier domain forward models with a function that allows us to turn our meta surface design into a spatially varying plus spread function. As long as that's differentiable, that forward model, we can do it. Okay, so I'm not going to go crazy on optics in this talk, but I want to just take you through how we do that for this particular proxy operator, which is a nasty, super non-differentiable function of the past. So we define a polynomial here. That's our design space. Essentially, that parameterizes the phase for a single wavelength in this particular design. So define here phase as a function of the radius from the optical axis. We then determine a nano pole structure. So these are these nano pillars that we design on our meta surface array that will impart that particular phase response. And we can map that now to the imparted phase at different wavelengths, get a multi-wavelength phase function that gives us the electric field that we can propagate back to the sensor and get the spatially varying PSFs. So now if you can make that entire process, which is typically non-differentiable, then we have a nice pipeline that we could back propagate gradients through and optimize for that particular design space, which is really only these polynomial coefficients in the top left here. So all of this hinges on this proxy operator for this phase to structure design. So phase to structure, well, I haven't really told you what our meta surface is so far. So meta surface consists of these nanoposts here, silicon nitride nanoposts on a fused silica substrate. So they are 750 nanometers in height, and then we can vary their diameter here from 100 to 300 nanometers. And so this is really what we optimize. So we can locally call this a duty cycle sort of. And so to ensure that we get a differentiable mapping from duty cycle to phase, because he tells us all right, delayed, we use RCWA, which is a Fourier domain method that we can locally solve Maxwell's equations. So globally, doing this for an entire array is going to be computationally prohibitively expensive. So that explodes. You can't really do it for larger surfaces than maybe 10 microns or so. And so we had to come up with a trick in order to make it injective, this function. You see the individual mappings from phase to duty cycle plotted in orange here on the right side. Can again fit a polynomial to it that becomes a differentiable function. And all of a sudden we can, in a few lines of code, come up with a differentiable model for this particular block here. That allows us then to make our entire pipeline differentiable, and this is 3,000 times faster than conventional full wave simulation. So for the first time, we can actually then, in a differentiable fashion, optimize these meta optics. You again see a time lapse of our optimization process here for a downstream image loss, right? So we combine this with a deconvolution network that allows us to then propagate gradients all the way through the forward model back to the design parameters, which are these polynomial coefficients. And then in the end, we can design a meta optics, which we did. So comparing here to the best existing one, which was from a couple of years ago, can do a lot better in terms of chromatic aberrations. And our nano camera on the right really achieves significant improvement in resolution and reduced aberrations. This is substantially smaller than a compound optic. You can argue compared to this big compound optic here, which is a lot bigger. And you're starting to get there, right? So this is still not perfect, but here on the right side, you see the nano optic captures of a full color image and the conventional camera here on the left side. Now, admittedly, this is a little bit cheating, right? Because as you all know, as image processing experts, like you see all these operations in the background. And I'm cheating here because I use a black background, right? So not really fair. We can do better by building an array of these elements. So stacking them all spatially, basically just on the cover glass. So we throw away the entire compound optics, right? And build our entire optic just as a thin 750 nanometer thick layer on top of the cover glass. So it's just a sensor and the cover glass, 1 millimeter bifocal length. That's it. And that actually starts to work. So here's some results for scenes where we're not cheating and we don't have a black background here. And by stitching together these measurements from the different lens sets here, we don't have any baffles between the lens sets, you can do substantially better. So here you have like an ultra flat imager that sits directly on the sensor that can get you better things. All right, so last optics piece here. So differentiable cameras also allow us to get to what I would call superhuman capability. So can we build a camera by modifying the optics slightly that allows us, for example, to see through obstructions such as dirt on the camera? Can we do that again by making the optics or solid block differentiable? So this is very relevant for applications such as this automotive case here, where we have a camera that sits behind a glass surface. So in this case here, a windshield. And we wanted to capture the scene and hopefully detect with our ADAS system that we are assuming here these pedestrians in the scene. So now occlusions from soil or raindrops even, and they're not occlusions or bugs on the windshield, can make this pretty challenging, right? So you could say, hey, well, I mean, we have all these amazing in-painting methods, but what do they do? Well, even if I manually segment out these obstructed regions, I can't do really well, right? Because I'm oftentimes missing context and it's tricky to in-paint for these methods, unless you make the region very large and then you hallucinate a lot of content here. So here on the right side, you see a painting by Llama, which is doing pretty well on regular scenes. So we can do this much better by, again, changing the optics, inserting an ultra thin layer that kind of like tailors the PSFs to a particular problem that we're looking at here. And I'm going to tell you exactly how we do that. And then using computation trained again in end-to-end fashion to recover an image here that is getting rid of these occlusions. So how exactly does this work here? So let's look at the scene here. The vehicle in the scene, conventional optics, focus light at optical infinity of different positions on the sensor with a relatively small point spread function if your optics are good. So now obstructions close to the optics result in a blurred point spread function. And so we have a relatively large blur here because we're much closer to the camera as the objects at infinity. And these get approximately alpha blended with the background. So now we plan to make use of this optical blur, actually insert an optical modulator again, building on these nano array optics from before, and then tailoring PSFs in order to do what we want to do, what we learn in the end. So what do I mean by that? Okay, so we can design a reconstruction network that takes the output, conditioned on the PSF, recover an image from it, and we can supervise this if we have enough simulation data with the input images with the loss function here. We can train this thing then in an end-to-end fashion and ask our end-to-end system here now with differentiable optics, with a differentiable reconstruction network. Okay, what's the best PSF plus reconstruction network that allows us to see through these occlusions here? Okay, in order to do that, I need to actually have simulated data with ground truth, some pixel accurate reference data that I do, and that one we can actually simulate fairly effectively. So here you see real photographs of obstructions in front of the lens, and on the bottom some simulation. So that's doable. We can do that with ray tracing if you want to do that better, or with a simple alpha blend formula. That is good. So what happens? So if you learn in this end-to-end fashion, we get this really interesting point spread function that I'm showing you here. So here you see from the right to the left an increasing distance. So on the left is the furthest distance of the infinity here, optical infinity. And on the right side, you see objects being close to the camera itself. On the top, you see a conventional optic So you see this out of focus blur as we're getting closer and closer to the camera. See this disc, that's the aperture shape as we're getting closer to the camera. And then on the bottom, we see the learned result. So what's happening here is quite interesting. Without any supervision, that should be a ring-shaped PSF, we get this chromatic ring-shaped PSF. So that the end-to-end training wants to spread out the energy as far as possible over the entire sensor, and then gets us an image, which I'm showing you on the right side for the occluder distance, which is 20 centimeter, which has all this content from objects close to the sensor spread out over the sensor, over the entire sensor. And then we get we turn this obstruction problem in a dehazing problem, approximately. And a random diffuser here blurs over the entire depth range, right? So this doesn't really help us, just as a comparison. So here's an experimental result in the lab where we manufactured some of these PSF modulators. And here you see the reference image. And now we've overlaid some occluders here, the glass surface. These are these diagonal occluders that we have here. Here's in painting. And you can see that we've got lots of hallucinated content that we can't properly recover with this in painting method. And you can get back a lot of this content with this designed optical modulator. There's not a perfect setup yet, but shows you that this is possible and hopefully convinces you that there's a lot of exciting potential in these end-to-end systems. You can do better than post-processing. So. All right, so hopefully I've convinced you that there is a big benefit, or there's a big open area by making parts of the camera differentiable that we haven't really differentiated through the past. And so far, these were all completely novel cameras, right? So you need to change your existing optical system, either define a new different optical system, or insert some modulators in the existing optical systems to get these going. So we've made this differentiable and then learned different optics. But what about cameras that we have today? Well, we can actually make the scene differentiable and come up with cues that we get, for example, from the existing capture procedures that we have. So what do I mean by the existing capture procedures? Well, let's take a step back. So if you look at early days of cameras and early imaging applications, we had these really long exposures, so we need to come up with tripods, right? Then we're able to make cameras a little bit better. We have these unstabilized setups here. Really today, it looks like this, right? So we got all our smartphones. That is the de facto camera. It's attached to a portable computer. Right? Now, in reality, cell phone photography also doesn't look like this because you're not static. But what actually is happening is that you have quite a bit of shake, right? Just natural, constant hand shifting from your instability of your arm position when you take a capture of, like, let's say 2 seconds or so. Right? So this is a cue that we can make use of. So we're wondering, can we actually use this long burst data and do some neural reconstruction with it, right? So can we make, by making the scene differentiable, use of these this natural handshake that we have in the images. So what we look at is 2 second, 42 megapixel high frame images that you get from your modern iPhone. So the iPhone 13 or iPhone 14 have these high resolution sensors with raw images that we can get. And just a little bit of shake, right? And handshake, folks have been looking at it in the past as well. So can we come up with a differentiable model that allows us with an RGB plus depth model to get a lot of data, particularly depth and RGB, out of these handshake measurements? And you can actually come up with this if you combine a neural model with a set of planes in the background. I'm going to take you through exactly that, how that works. So, so you see reconstruction from a little bit of handshake. You see the depth recovered and also the camera motion. And we can obviously then use this depth that we get just from the camera motion, no other priors, no learning from mono networks to do funky things like repositioning, refocusing, relighting, of course, right? Again, just from handshake, no other data priors being used here in this case. We can completely re-render the scene and use the effects that you want to see on a typical mobile application. All right, so before we go into the details of the model, like, well, you guys all know NERF. At this point, we've all seen the different applications, so why not just apply NERF to this? Does this work? Well, NeRF requires on multiple views, right? Requires positions of multiple views to be used for density estimation on a particular object surface, right? So we basically iteratively refine the positions, density of points, minimizing a photometric loss, which is the main training objective here. With some regularizers, there's a lot of thousands of different methods that folks have coming up with that are doing this effectively. So if I have diverse enough views, that I can use this photometric loss only to estimate the density of points where they are. Now, in our case, this is slightly different, right? Because we have a relatively small parallax, so only a few dozen of pixels. So here's our capture app. We get rotations from the gyro, the timestamps, some focus metadata, and here you see a long burst output. So we get these 32 frames here of raw data. And if you look at the parallax that we get, then this is only in this case here for an object that is relatively close, about 28 pixels, right? So not a lot to work with. What happens here with our NeRF problem? If someone asks me, hey, what kind of this negative NeRF in this case? Well, we're turning this NeRF problem from a multi-view photometric loss reconstruction problem into something more like this here. Right? We're capturing everything almost from the same points here. So the density estimation with conventional NeRF becomes super tricky. Right? So you get really bad results and have ambiguous and inconsistent depth if you use these volumetric models just by itself. So if I take a really good method, instant NGP, here shown on the left side, and fit it, this doesn't really work for both the RGB data as well as the depth data. If we take our model on the right side, we can do substantially better here. I'm going to tell you exactly how we're doing that. Okay, so we start by sampling a point coordinate, U and V here. And then we generate a positional encoding with a multi-resolution hash encoder. So following neural NGP idea. And we can learn then the positional, the pieces of the positional encoding. And we pass those through an MLP, which gives us an implicit representation of a 3-channel RGB image. So basically, it's that variation of an instant NGP model for the RGB data so far. Right? So nothing. Okay, so now for our depth, we use a similar approach where we again use a multi-dimensional encoding, multi-dimensional hash encoding. But here we do an important trick. We use a per encoding weight mask that allows us to weight these individual encodings from coarse to fine throughout the training. So we say at the beginning of the training, we slowly ramp up the contributions of the coarse grid and then slowly add in the positional encodings of the finer grids. So that gives us a natural way to train in a coarse to fine manner. So you see at the beginning that we only use the coarse weights, right? So the multi-hash encoders of the coarse grids. Then we slowly refine this. Pass those through an MLP, and that gives us our depth so far. All right, so the tricky part comes in when we want to model background, where we may not even have any parallax or objects that are far away, or you don't have any texture. So we simply fix that by adding a plane here, because shakes on a plane its name. We combine that with our depth, and we get an implicit RGBD model, which has depth both for close objects as well as far away objects. We can sort of separate it between these two components. We model then camera motion with a spline. So again, something that we can make differentiable. The rotations we already have from the gyro, those are reliable enough. And then we capture our long burst data. We want to fit that. Right? That's the main loss here that we optimize at test. So we have these n frames. We got the rotation and the translation. So now we can reproject our implicit RGBD model to each of the camera coordinates of these frames. So frame n, for example, with respect to the point in the burst frame. And we can keep on going and define, again, just the photometric loss on this output here. All right, so far, I've shown you a model that is fully differentiable. So we can backpropagate this loss all the way through the motion, image, and depth components, jointly optimizing all three. Now, let us have a look at how exactly this works. So that's the important step here. So this reprojection step, I'm trying to convince you that just with photometric loss, you can do all of these optimizations jointly. All right, so assume we have a one-dimensional camera that I'm illustrating here, and points on an object. There are D1, D2, and D3 that I'm showing you here. So if you apply now a known rotation and the translation to the camera, we can triangulate exactly. So here's the triangulation, and triangulate exactly where these points would land up on the new frame. So if it's really the same frame, then there's no photometric loss. Now, if the depth itself are not correct, then they sample here, so here they're incorrect, two different positions on the camera image that we want to fit to. So they incur a photometric loss that we can use to then backpropagate our implicit RGBD model. So this allows us to optimize both the RGB as well as the depth itself. So, okay, so let's assume now that the depths are correct, but the camera motion is wrong, right? And this again produces a per frame photometric loss, which we can backpropagate here to update the motion model. And so we can really optimize both jointly together with this particular model. And that's how we designed it. So here you see the optimization on the left side of the motion, as well as the depth here on the right side, just by this handshake. Okay, so why does all of this matter? Could I just use a mono depth model and just predict depth? Well, let's have a look at this particular object here, where we took a ground truth scan of these objects, the dragon, and this other object here, this GURD object, and you see that the scans look as follows. So these are the ground truth scans. Now, if I take a state-of-the-art model, MIDAS or any follow-up model, then you get really nice looking depth maps, right? So using a data prior and learning from a lot of depth maps gives you the really nice images. But unfortunately, if you go and reproject them into 3D space, you see that these are incorrect, right? So I don't have scale accurate depth here, only have depth that looks good, but is not accurate. For example, I see that my GURD object is kind of smushed a little bit. I see that the dragon's face is also smushed together, and the wing here is completely disconnected from the rest of the body of the dragon. And just by using this parallax information from these long burst captures, we can do substantially better and fix exactly these issues and get nice and accurate depth. All right, so let's have a look at a bunch of fun examples here that we can do with our app here. So we can get depth from this dragon, recover its structure, and since we have the background with the plane, we can so easily remove the background directly in the model and do fun animations and change the objects here. You can do real lighting here. This is, for example, a metal statue, where you can get also an accurate depth here of the particular object. And segment in the same way as before. So just using the plane model that we had from before to replace the background, do matting essentially, and relighting with this RGB depth model very accurately. Just by using our implicit representation consisting of the foreground depth and the background plane. So here's an object with again these two pumpkins placed on a plane here to be fit to pose relatively accurately. There's an animation of what we use at depth. So okay, so let's now look at an edge case, right? A really tough challenge, a 6.5 meter tall temple statue is really far away. So here you really only have a couple of pixels of motion parallax. And even in this case, we get somewhat reasonable depth that we can actually use then in our application. So even for just a few pixels, by using this implicit fitting, we get a pretty decent output. All right, so we're actually presenting this work at CVPR as well. So this will be a fun presentation this week. All right, so the last part that we haven't made differentiable so far over our entire camera is really the post-processing. So far I've talked about captures with conventional cameras using handshake, redesigning the optics. There's other work in the past that we've done on redesigning the sensors itself and the ISP. But what about post-processing? So I have these amazing raw images now, and example released their iPhone 14, pretty much everyone has access to these now as Apple's Pro RAW captures. These are 48 megapixel RAW captures. And typically, as an artist or a photographer, you have this post-processing stage where you do tone mapping according to your artistic likeness, right? And so this photo finishing is oftentimes produced in existing software, off-the-shelf software, such as Adobe's Lightroom, or you can build your own tone mapping application that does this effectively. But Adobe has re-cornered this market. So Lightroom is being used to do this photo finishing application. And yes, as a photographer, you would basically take your RAW and then you map it either to the style of Blade Runner here, or you map it to the matrix, depending on what you do. Right? So you can fix it depending on your artistic styles for the same. Now, this block here is really not differentiable, right? So this is partly legacy code. Folks have been coming up at Adobe with this for a long time. And you cannot differentiate through it and use this in your end-to-end optimization, right? Which is something that you really want to do if you want to keep the photo finishing as part of this application. Now I'm trying to convince you that you can make even that block differentiable by again using this proxy idea from before. So the idea is that in Lightroom, there's like a few components that we can each represent as proxies. So it's basically an elevated ISP that has a bunch of blocks, contrast stretching blocks, saturation blocks, and texture blocks that we can each fit proxies to, that we can then chain together and train in an end-to-end fashion. If you train one proxy by itself, you do that, for example, to Adobe's Camera Raw as well, this will not work. This is not good enough. Take your favorite UNet or modified UNet or whatever architecture you'll take and it will not work. But by decomposing a pipeline into its individual blocks, we can actually make this thing differentiable with relatively accurate outputs and then differentiate through it. So the idea is that you need these tab outs. So you need to be able to have at least access to the pipeline, not to the code of each individual block, but the outputs of each block and the inputs to the next block. If you have those and you can sample those, then you can get tap outs of this pipeline that you can use as training data to train these individual proxies. And this is what we had as access. We were able to get data out of these individual blocks of the pipeline, not the individual code itself, which even if you do auditive for the code is not differentiable in many cases. But you can use this then as training data. And the key thing is here that you give also your proxy as input image statistics. You give it the histogram or there's some other image statistics that allow it to learn from the statistic blocks itself instead of learning it from the data itself, which would be a very large corpus of natural images. So initially, when we tried this, for example, for this texture block here, you end up with a vanishing samples problem. Because of the skewed training that are produced by photographers, you get parameters and images that kind of fit this typical, here we have the RGB cube distribution that you do not want to have in your training data. So you kind of have to force your training data to be more diverse and sample all kinds of diverse points, all these tab outs in order to get representative enough training data that you can use for training. And so this small cube here now covers the RGB and slider space that we want to optimize over. Then we can train it in isolation and chain all of these individual proxies together. So we're able to do that and then get one differentiable model of the entire Lightroom application. And this worked in practice really nicely. So we can use these gradients to do a bunch of different cool applications. So for example, we can do slider regression. So what's slider regression? So let's say I have a raw image, I have some unknown setting that gives me an output image. That is the photo finished output here of this particular photographer that came up with this setting. the matrix blade runner or a neutral style here that I can then apply on the video that can be conditioned on the previous frames or a particular artistic style. So in summary, we have come up with a way to make Lightroom as post-processing step also differentiable. So that brings us to the end, and we have convinced you that it's pretty exciting to make all of these different blocks differentiable. The camera optics, build new optics, existing compound optics, allow for new tiny cameras that can make optical stacks super flat, use new cameras that allow us for what I would call superhuman vision, and make the scene differentiable and potentially the post-processing as well. If you bring all of these blocks together, we get an entire differentiable camera stack that gives us all of these opportunities. Thank you.
Thank you for this very good presentation. Now we are open for questions. Any questions from audience or remote?
So I have a question regarding the meta lens, it's very interesting topic. For the simulation, so I see your the aperture size of the meta lens is 300 nanometers, basically already a diffractive optics.
So the aperture size of the small one is 0.5 millimeter, and another one that I showed you on this array that was about 1.5 millimeters. Yeah.
So the answer is for because of the pixel size of the camera or the sensor, right? It can vary from 0.56 micron
Yep.
to 1.6 micron. So for your simulation, so once you change the pixel size, do we need to rerun the simulation?
Yeah, so this is still assuming relatively large pixels. So here we have super large pixels, so 3.8, almost 4 micron pixel pitch. Just because we're still also finding light efficiency because we have these relatively small apertures, right? But that is one thing that in the array implementation, what I briefly showed here, we have largely overcome, right? So there we're at 1.5, 2 millimeter apertures, right? So we have less of a problem there.
So when you run a simulation, you run only 3 wavelengths or you run the full?
Yeah, so we had to run the entire full wavelength spectrum because otherwise it doesn't work. Okay. So this is really important. So like a lot of the technical juice is actually in the approach how we specifically can sample over the entire wavelength spectrum, because folks have been only doing these like point-wise wavelength sampling, which is easier, and it doesn't really work in the wild now.
Yeah. And so manual actually is at 100 faster than the improve the station speed. So manual is actually how fast you see in the really nice variation of the flowers. How long does it take?
How long does the reconstruction take, or the so the reconstruction is still on a relatively big GPU, so I haven't really optimized this, but this is still real time. So we get what is it, like I think 30 millisecond throughput, right? So you do get real time outputs on a big GPU from this. Now there's still a lot of work in bringing it on the mobile devices, right? And do not run it on a big NVIDIA GPU, right? But yeah, it's just a proof of concept to get started.
I just be very impressed. Thank you.
Thank you.
For the slider registration, when you upload Lightroom's, many different settings could lead to very similar looking photos.
Yeah.
So how much ambiguity did you notice? How much, what would be the variance that you would get if you tried to randomize the network address?
Yeah, so I mean, it depends really on the particular ISP, right? So we learn this differentiable mapping, right? Which, and if you use these neural networks to learn these proxies, it's kind of nice because they come up with this smooth interpolation of the different spaces in the outputs of our ground truth ISP that we want to model in case. Right, so they make the optimization much more well-behaved, right? Now, that said, you can end up in different local minima using S3D. So we simply solved that by different initial settings here. So different random seed points as initial points, and that was good enough for all of the applications that we tested. But of course, you could come up with ISPs, like let's say, for example, come up with an ISP that has a binary switch, right, between completely different logic for one setting versus the other one, right? And then I've sort of compressed two ISPs in one or even more, right? that becomes then pretty tricky. It can really easily end up in local.
Do you think you would be able to extend the work to estimate the post-processing parameters that people would also use, and like, for example, like changing the fragments?
Yeah, exactly. So we can really nicely fit, for example, to the stylistic choices of a given photographer if we have a data set, right? And for that data set, if we have the paired inputs and outputs, we don't even need the settings, right? So that one we can easily estimate. Right?
Thank you.
I guess I do have one follow-up question on that. Is that like we talk about trying to proximate, make a proxy for like say, let's say Lightroom pipelines. You actually you tap out some points, and it's kind of like a semi-black box proxy.
Right.
I'm wondering how hard it is to do like a fully black box. Like say I buy let's say Qualcomm chips. I only know input output there, bunch of Paris injected tube, but I don't know in between how hard that is.
Great question. So it really depends on the particular ISP. So we actually did this. So a lot of the automotive ISPs are actually pretty easy. So those ones you can completely approximate with a single proxy, but some of them, the mobile phone ISPs are relatively big and mature at this point, right? So for those ones, it'll just not work. There's a lot of really complicated ISPs, like the example with the binary switch is one that's really nasty to handle, right? So you kind of need to know or have at least some tap outs, right? So you cannot get away super easily with just a black box model, right? Because you need so much data otherwise in order to get there.
Okay, thanks. And also, I thought about your differentiable optics that's really inspiring, and we're also trying to think about something like that induction. And one question I also have on that is that all this kind of differential optics in the end is people using this kind of like a gradient-based optimization. And in deep learning community, people discussing about like whether you can achieve the optimality through gradient descent, and people conclude like say if the number is big enough long parameters. The chances you'll get like even through very simple gradient descent, the chance you'll get optimal order. Location will be reasonably good. But I'm just asking, do you think like entirely when we use this gradient descent for deep optics, do we really get the optimal solution, or we are still just actually something room there just for optimization to be improved?
Yeah, no, there's big room, but it's seeing exactly the same the same conclusion, right? The more parameters we have to play with, right? So that's why these meta optics are really exciting, right? So you can play around with polarization, you can make these asymmetrically shaped nano optics, you can control phase and amplitude at every position, right? All of a sudden you have so much more design parameters that you can play with, right? So that really allows us to take one of these local minimums, right, and come up with a good one, right? So the more parameters that I throw at it, like the fewer I have, the harder it gets, right? So that's why it's actually pretty tricky to get these compound optics, which don't have too many parameters, right? But it's nasty parameters, right? You have the categorical glass variables. We have another paper in CVPR where we're looking at this, and this is so tough to get this right. The glass surface, it's not a lot of parameters, but it's tricky parameters, right? So this is much harder to get right than throwing a lot of parameters. There we can come up with good proxies and use it that way. So the insight is here that traditionally, like stuff that has been traditionally really hard on the optics side, is actually much easier if you make it differentiable and vice versa.
Thank you so much. That's very inspiring. Thank you.
Thank you so much. We have a BP here for sure.
Oh, thank you so much.
Now we move to the next keynote speaker. The next keynote speaker is Prof. Tian Fanxue. Tian Fanxue is Vice President, Assistant Professor from the Department of Information Engineering of the Chinese University of Hong Kong. Tianfan's research focuses on computational photograph, computer vision and graphics, and machine learning. Today, he will share with his research on how to build a smart camera systems. Tianfan, the floor is yours. You want to use your laptop?
Can I use this one?
Okay.
Right. Everyone, it's my great pleasure to be here and share some of my thoughts about the smart camera design. So before that, I just a very quick introduction of myself. So I'm currently assistant professor in Chinese University of Hong Kong. And before that, I spent 5 years in Google research, particularly in GCAM, mostly working on computational photography and the cameras. So I have quite some experience also about all this computational photography techniques being used in industry. And I'll also share some of the thoughts on that in this talk. So, talk today. So, like we are in this era of AI and big data, and everyone talk about smart cameras. And like many people think smart cameras just saying let's apply some AI or machine learning these days to images. For example, we have an image, you run a detection and see this tower, and also like in computational photography, we also use that a lot. Just saying that we do a lot of like image, deep learning based image processing, like a face verification, stuff like that. But I think this might not be enough. Let's say we just apply images to machine learning algorithm to images. For example, in this image, if you run, say, like object detection, you see nothing, but actually there's a bike coming out. And because in the first frame, just don't get any signal to start with. There's no way, or at least to my thoughts, it's really hard. You really detect this just use any machine learning algorithms. You have to capture these signals at the very beginning in order to really detect this. And this is actually from videos of a very badly fatal car crash. So that's kind of which tells us we might need to inject this kind of AI system, machine learning system, into our camera design and physics. And you have to do a lot of work on this, so I don't need to emphasize why this is important. But the kind of a design in my mind is say, we normally, before that, we think we have an image, cameras, capture an image and run machine learning models, which I believe a better solution is that we combine our machine learning with our cameras and your entire camera and the machine learning together, and that's a real smart camera should be. So this is my view of how this could be done. I just talk us through. First off, I just want to introduce a normal camera pipeline, how it works. First, we'll have a scene. You use the sensors, either normal sensor or this kind of a fancy nano lens, and we capture some images. And we throw these images into some image processing pipeline, either software like Lightroom or like these days people use a lot of ISP and image signal processor to generate it in the normal image we see. And we run detections or some fancy editing on top of that. So in this whole pipelines, there's a couple places we can use the machine learning to help us. One is on the capturing side. Machine learning can help to combine what I call multiple source information. I will give more examples to see what this multiple source is. But in general, on the capturing side, we can try to get more information and combine it together, use machine learning. And on the processing and recognition side, I think there's two, for machine learning, there's two very important things. First, where your training data comes from. Second, what network you're using. And these days, when people say machine learning is all about deep learning, so what network structure being used. So that's the three topics I'll talk about today. So let's start with some capturing side. Again, let's start with low light imaging. This is a very low light image captured using these cell phones, and because it's very dark, you don't see too much. For example, here I cannot see anything. I guess probably most people don't. Sometimes when I show this image, someone can guess what it is, but hard for me. So, but if we can change a little bit about the whole capturing pipeline, we can get an image like this, which is same cameras, still handheld, but it's very nicely lit. This the little corner of the bar, and there's nice flowers there. And this is what we said, like how machine learning can help. One thing I would like to mention is that it's not say we have a train an algorithm and say take this image as input and generate this, because many information have been lost at the very beginning. You cannot just train one image to enhance like this. So we really need to make a deeper change of the pipeline. So how to do that? Again, in low light, the reason image become dark is because there's less photons being hit into our sensors. In good lighting condition, you have enough photons, so it's bright. Low light, you don't have enough photons, so it's dark. So there's a couple of ways people trying to solve this problem, saying like we all should be very familiar with exposure correcting. You capture a bunch of photos with different exposure levels and try to fuse them. And there's techniques have been developed there for 20 years. But like until recently, this actually been rarely been used in our mobile cameras, because in presence of motions, using different exposure level images with different exposure level, it's not very easy to be robust. So in most of the, previously, when people trying to capture trying to still capturing in low light conditions, people mostly just trying to extend your exposure time, but definitely that will also bring us some motion blur. So very recently, this problem being solved, we use this kind of what's called burst photography. The idea is very simple. You just capture a bunch of images, same exposure, so it's easier to align and fuse them. And all these images kind of underexposed, so you don't lose some details and highlights. But when you fuse all of them together, it can. Another thing is underexposed, so you don't also have this kind of motion blurs. But when you fuse them together, you still get enough signals to capture all these low light conditions. So my previous team in Google, GCam, they developed several algorithms on that. Initially, on 2016, there is HA plus algorithm, which on the left is normal capturing, and on the right is the result of fusing. I think it's about 7 frames, and you can see it much brighter, and some of the details also being reviewed through this process. And later, we push it even further to make it more extreme. To build this nice eye algorithm. I mean, again, it's using multiple exposure together, but we do more aggressively, saying in really low light condition, we also extend exposure time and also do better and more aggressive fusing. So you can really capture something you barely can see in low light. For example, on the left, I can barely see anything. And on the right, you can see this very nice, this is the very nice bookshelf, pianos, very nice one. So this kind of power of one of the power of the fusion on the capturing side is to just capture more images and trying to fuse them together to boost your signal to noise ratio. But on the fusion side, it's not only for that. Not only we just extend like a signal to noise ratio, there's more information we can get on that. For example, this is another videos we captured where there's a very strong reflection. I think maybe I'm wearing the same t-shirt like this. Yeah, very similar. But there's very strong reflection, which is undeniable. And there's a lot of like a single image reflection removal. But you can see when this reflection is really strong, differentiate background with reflection is very hard. But once you capture multiple frames, things become easier because you can see this kind of a reflection, which is basically this kind of a t-shirt patterns, moves much faster because of motion parallax compared to the background. And just fuse them together and can remove it. So like an originally very challenging task, single reflection removal can be easily solved with multiple frames. Again, this even you have 2 frames can do the same thing. Because the reason 2 frames is interesting because of most of the cameras these days, some cameras have at least two cameras, not 3. And there's one interesting example in this one is that if you look at a single frame, this white dot here could be considered as a part of this kind of snowman's like a he's holding a ball. But if you look at 2 frames, you can definitely see, okay, this is not actually part of the snowman, it's actually a reflection part. So this actually tells us shows us like sometimes we really need multiple information to solve some kind of ambiguities. So that's one part when I say multiple source is that we just fuse multiple images of the same type. But there's much even more we can do on that direction. This is a very old work in 2004 by Rick Skleski and Michael Cohen, trying to do this kind of non-flash photography. Is that when you capture an image with flash, definitely you don't see any noise, but the color is often off. And if you turn off the flash, the color is better, but there's a lot of noise. So you just take advantage of both and try to fuse them together, get color from non-flash and the details from flash, and you get this very clean, nice image, but also vivid color. Simple idea, but just works pretty well. And we can further extend that is that people know that in really low light, infrared camera with infrared flash can actually capture very nice image. I'm not sure how many people are using this kind of surveillance camera for babies. I have one in my home. During the night when I cannot see anything, the camera will turn off this kind of it's an IR flash, and I can use my cell phone and still see my baby clearly. And that's kind of power of this IR. But again, IR image have this very bad problem is that the color is pretty off. So again, combine that with a noisy RGB image, you can get a clean image, but also with a correct color. So that's another type of a combination. We can just combine the different cameras to capture a different perspective of the same thing and try to fuse to get them together to get a better quality. And people can even push this direction further. Nowadays, a lot of people talk about event cameras. If you're not familiar with that, here's a very simple diagram to show that if there's standard camera, just to have a static capturing, static intervals between each capturing. So when the object is moving really fast, it can only capture a few snapshots, which event camera will generate a stream of the output, a stream of event only report when there's a movement like this. And because only reported the movement, it can capture in a much higher frame rate. But again, this is only, it can only capture dynamic image, it can capture static. So standard camera can capture a full resolution static image, and the event camera can capture high frequency, like a high frequency dynamic event. So both have this advantages. And again, computational photography kicks in, and we can combine them to generate this very nice frame interpolation results. This is a work by David Saramis from the University of Zurich, which is basically you have this low frame rate videos, and in the middle you have this kind of a high frame rate videos by event cameras. And if you just do normal frame interpolation, it's very hard, particularly for this fire, because you don't know how fire moves. But with this event camera as intermediate information, kind of very nice interpolation result on the right. So this is another examples, two cameras, different have a capture different perspective and fuse them together, can get very nice results. And you don't even have to use multiple cameras or multiple exposures. Even just single exposure could work. Here's one example. So normally when we have this kind of RGB camera, it's have this Bayer pattern. But in practice, many sensors have this kind of what's called a dual pixel setup, which will split some of the green pixels into half. So each pixel becomes a small micro baseline stereo, like this one. Here I just showed an image of the left and right images of these split pixels, and you can see that it will have a sliding shift because of that, because you can consider this kind of micro baseline stereo. And by combining all this information together, you can estimate the depth map and also calculate the already focused image. Just remove all the motion, all the blur, like a defocused blur from it. And this is not like any like the machine learning, like a really fancy trials to understand how blur kernel is. It's just all this blur information is already embedded in these 2 pixels, and that is solve what's actual blur kernel for each depth values. So again, even single frame as a single capture with some special depth design, you can still recover some kind of information from it. So that's one part, is that I think we can be really creative in kind of the camera design, capture design to capture more source of information and trying to use computational border to fuse them. Okay, that's for the capture side. Now let's move towards the actual processing, which is our neural networks part. So there's 2 things, as I mentioned, training data, network. So for training data, I mostly want to talk about how synthetic data are being used to train all this neural networks, particularly for image processing. So typically, when we say we want to design a network for image processing, it normally looks like this. You have some input, a network, and you have an output. And for example, denoising input is a noisy image, output denoise output. So in order to train a network like this, you need a pair of a noisy and denoise output. So how do we get this pair? So if you talk to the, like say, computer vision folks and say, okay, that's easy, you can just label it. It's, for example, for object detection, you can just label all these bounding boxes very fast. And then some experienced laborers can do it at like a 1 image just in a few seconds. So again, people label tons of images, like the internet. There's millions of images labeled this way. However, if you come to the computation, like image processing, that's hard. Like for example, if I ask photographers, let's try to denoise image. What he will do, or he or she will do, is say, I will zoom into each patch and tune all these kind of denoising parameters and try to find the best one, and then go to the next one and do this in iterations. And it takes even 1 image. When we walk to some photographers, it takes like several hours to just denoise 1 image. And that's not scalable when you say, really, I want to build millions of images for training in this way. There's another approach, like people saying, like for denoising, we can just capture really long exposure time, so that because it's exposure long enough, there's no noise at all, and use this as a pair of training data. But again, you need to really capture those images by yourself And if people have done that before, you normally can only capture less than 100 images per day. And to make things even worse is that there's so many devices these days. So here I just only list all the possible cameras. I think it's back to 2020. I think it's only back to 2021. So there should be more cameras these days, and I list all of them. So each camera has its own sensors, lenses, different statistics. One models may not transfer well to the other. So all this does bring us to questions: how can we collect this? Like if you collect ourselves, we can only do like 100 images per day. But actually on the internet, 3 trillion images being uploaded. Again, this is the oldest statistic. Today will be even more to the internet. So can we utilize this gigantic images from the web to help us? So that's actually many people doing these days is that let's use synthetic images for training. And the way to do it is very simple. Is say you have a clean images, you try to add some synthetic degeneration, for example, add some noise, and you use that as your input-output pairs. And then you can train a network on that and to like say, to do the denoising. So it ends up like to build a better networks. The key is to how to correctly generate this realistic degeneration. How to generate this degeneration realistically. So this is very task specific. I'll just share some of the of both our works and other folks works on that, and just to give people an idea what might be important in this direction. So let's start with a very simple case, which is denoising. So we all know that there's a very good noise model for like cameras for the Gaussian Poisson noise like this. But the only problem is this Gaussian Poisson noise only applies to what we call raw image directly from our sensor output. And unfortunately, most of the images we saw these days and raw image, but sRGB images go through a really complicated camera pipeline, and you can't expect the same distribution still holds in the sRGB space. So here's one simple trick we did before, is that since we cannot like add model noise for sRGB space, let's try to invert the whole camera pipeline. So this is a very simplified one. I like invert tone mapping, gamma, color correction, and apply the mosaic pattern back. So to convert sRGB back to the raw space. And then we can add noise. And then we go through camera pipeline again. Then in this way, we'll get a little bit more realistic noise in here. Again, people may argue you cannot just invert pipeline like this. Camera pipeline is really extremely difficult. Yes, but that's at least one step closer to the reality. And that's just more step closer, makes quite a bit of improvement in the denoising qualities. Again, there could be much better way to do it. And I think like there's definitely a lot of rooms people can think more better way. How can we better model the noise pattern in real sRGB images? And the more we can get close to reality, the better quality we can achieve. And this is also one of the work by Jane. She just talk about. She didn't mention about this part, but this is also very nice work on the raindrop removal. Again, when trying to remove raindrops, you first need to simulate how raindrops on the images. So you need to understand what raindrops should look like. For example, in this work, they have analyzed like when there's heavy rain, there's different raining patterns. Or there could be a multiple layer of rains when there's very strong rains. So it's not only one direction, but multiple directions. And when you take all this more realistic modeling of realistic rains, you can improve your algorithm accuracy when you actually train your models. So that's only on the image space, and this is sometimes even more when you really want a realistic simulation of what happens in reality, you also need a bit understanding of 3D geometry. For example, here's an example of trying to simulate some of the reflections on the image. And if you know some, I won't go through some very detailed the modeling, but basically the reflection how being added to the image is actually related to how that reflection, the distance of reflection to your cameras, so that changes of the blurry kernel when you're trying to image the reflection. So what they did in this work by what they did is that they get an RGB image and run some depth prediction to get some synthetic depths. Again, you may argue this is not the correct one, but still one step closer to reality, and use this synthetic depths to synthesize a more realistic reflection, and that helps to improve the quality. And furthermore, we can go even more extreme. We just use rendering engines, like all these graphic rendering engines can really generate really nice rendering results, and we can use that for training. And for example, this is one of what we did before. We try to steal for reflection. We just add windows in this synthetic engines, and then we can generate this image with and without synthetic reflection pair like this. Although this image doesn't look super realistic, the network actually somehow have this kind of generalization abilities that if we train on an image like this, when we apply real images, it can get some very decent results. And also, this is one of the work they just talk about trying to also simulate this kind of a low light image from the normal lighting images for like some high level tasks. One last, just very briefly mention about this. One last is also we can also simulate a flare, and for that you also need to understand some optics because all this flare you can see when you image through this really strong light source. This kind of flare, if you want to better to simulate it in your engine, you need to really do some optics simulation. So I won't go through some details, but normally we see a flare like this. It has two sorts of flares. One is called this kind of scattering flare, which contribute all this kind of diagonal shaped flare patterns. The other is kind of this reflection flare. Basically, you hopefully like directly goes to the sensors, but actually there's an internal reflections, and this contribute to all this kind of colorful reflection patterns. And if you can better model this, you can actually generate better. You can generate a good flare patterns for flare removals, and that's one of what we did before, trying to use this kind of a object simulation to generate flare patterns, and it works pretty well when we extend it to real images. And at last, I have one more story to share about dataset. We'll talk about that. So this is one of the work we did before for video processing, trying to do video denoising. And we built this data set called Vimeo 90K by that time just for video processing. And we collect a lot of videos from Vimeo website. And one interesting thing I would like to share about this one is that after we published this data set, we found that it not only used for video processing, but also used a lot in video encoding. Because when we collect this data set, one thing we did accidentally is that we used all the videos in this data set. We don't use any temporal encoding, like say motion predictions in normal video codings. And it turns out this one particular aspect of the data set is very useful for those people who are working on like a video codecs, like a neural network-based video codecs, and it works pretty well. So I just want to share this story just to show how dataset can make impact to our field. Even just one small change when we design this video dataset actually makes some changes to our field. So I think really for computational photography, a good design of dataset is very critical for the community. And at last, I'll talk a little bit about finally we come to the point of the algorithm and network design. So for that, the point I would like to talk about is that we have seen a lot of convolutional neural networks, transformers in our not only for convolutional but for in general computer vision communities. But one thing I would like to argue is that even before this neural networks, we actually have a lot of image processing algorithms. And I think we can learn something from those algorithms and combine with these deep learning networks. So I would like to share a bit of some of the works in the community trying to push in this direction by combining the traditional image processing with neural networks. So one thing I would like to talk about is the when we talk about the image processing, one simple way, if you try to model point operation, is what's called 3D large, which is very simple. It's basically a three-dimensional volume by saying if you have a mapping from RGB to RGB, then you just represent your mapping through this kind of three-dimensional volumes to record for each location what the output RGB value should be. And this is very widely used in many, like say, Lightroom processing pipeline. And it's very efficient to apply this to image. So there's a lot of works trying to, recently there's quite a few works trying to utilize this kind of representation for image processing, combining with neural networks. For example, this is by Lei Zhang's group. And what they do is that when they're trying to enhance an image, they don't directly train, say, let's have a neural networks, input image, output image, neural network in between. Instead, what they train is what is called like a weight predictor, which given this weight will combine based on predefined 3D lookup tables. And after combination, they apply this lookup table to a high resolution image. So you don't have to really train an end-to-end neural networks. You only need to predict this simple 3D lookup table. And because of this design, this algorithm is really efficient compared to some baseline. Let's say this there's about like at least 10x, if not 100x acceleration, and the quality is quite reasonable. And also, not only 3D large is one widely used. There are also another very widely used formation is this kind of like this color curve. Like when you're trying to apply a change to an image in Lightroom, you can tune the color curve. And again, in order to enhance an image, you don't have to really say your end-to-end training. You can just train a curve predictor to get low-res image, predict the curve, and apply this curve to the full-res image. And this is by Sindustin, trying to build a curve-based enhancement like this. And here's another work we have done before, is trying to also combine traditional image processing with neural networks on style transformation. So here's a normal style transformation work we do. Like if you have a content image, a style image, you have a network and output stylized output. And again, when we try to apply this on high resolution image, it's not very efficient. So we were thinking, how can we make it even faster? So again, we want to try and process these tone curves. So one thing you can do is that, like say, if you plot the input and output intensity like this, you'll find that at least in this task, the input output mapping is not 1-to-1. It's more complicated mapping. So you cannot approximate this through a global tone curve I mentioned before. But what you can do is if you zoom in into one patch, or particular patch here, you'll find that if you plot input output intensities for each local patch, it's more linear. So for that, that basically tells us you can approximate the mapping from input output locally using a simple curve like this. And using this idea, then what we can do is that given an image like this, you can chop that into a small block. And for each block, you can further chop that into each small things. And combine this all together, you get a bilateral bridge, which is proposed by Kevin Chen in 2017. In this structure, I won't go through the details, but basically you can consider a bilateral bridge is just a set of curves will be applied to the image. And utilizing this, you can design a style transformation network like this. You only train a network taken to low resolution style content image and predict this bilateral bridge, which is a basic set of curves, and apply this curve to a full resolution image very efficiently to get a full resolution result like this. Because this kind of decomposition of low res and high res part is really efficient on the 5 milliseconds, even on like a 12 megapixel image. And you can preserve all the content, like all the details in the input. For example, this is input, this is stylized output. And if you zoom in, you can see all the details is well preserved. And this is on a resolution of 12 megapixel images and all done in 5 milliseconds. And that's kind of a powerful powerfulness. You try to combine and traditional computation, traditional image processing pipeline with neural networks. And again, people or this idea is originated from the Michael Garvey's works for HMNet. They use that for mapping process. And because it is so efficient, we also try to push that. We also push that on a Google Tensor chip, and now it's being used for HDR mapping. I'll probably skip this one. And one last thing I would want to say in this direction is that before that, I just to talk about how to combine one particular processing algorithms networks. There are even more fancier things people can do, saying that actually, if you're familiar with kind of image processing pipeline, it normally consists of different modules, say denoising, tone mapping, white balance, blah, blah, blah. And this is by Professor Professor Jingwei Wu. And what they did is that they, instead of saying, let's train a network to approximate all this, they say, let's train a network trying to use each block, like denoising, tone mapping, white balance, as some small parcels. The network is actually trying to combine these small parcels together to build a customized pipeline. Say, given an input, the network is trying to do a search, like a neural networks architecture search, to find a best pipeline that is designed for a particular task. And here's some examples. So, for example, they find that for SID, which is a very popular image denoising pipeline, the denoising data set, they find that this is the best pipeline for this task. And on sensor ISP, they find a slightly change of pipeline can give a better result. They're shifting the order between the white balance and the gamma correction, and that gives slightly better results. So here's another level of control that we can even use machine learning to like move different pieces of traditional pipeline together to build an even larger pipeline. And they call it a reconfig ISP. So I think there's quite a lot of works in this direction, combining the network and the traditional image processing to make our design more better fit for this image processing task, and also can make it more efficient. So at the very last, since we have about 10 minutes, I also want to share a little bit more thoughts about what I think there might be some interesting future direction in this smart camera design. So one thing I mentioned quite a lot in this talk is simulation. So I think simulation is really important in our community because, like as I mentioned, creating ground truth data is really hard. And this is one image I got from Tesla AI Day, which is pretty inspiring. So when they trying to simulate, trying to build this kind of automatic driving data set, they trying to simulate a bunch of artifacts normal sensor were capturing in reality, like sensor noise, like some like a photometric calibration of sun and the sky, virtual reflection and all this kind of stuff. They're trying to simulate in their training data set, so the algorithm will be robust when the actual camera see all these artifacts in reality. So I think that the better we can build a simulation pipeline for this, the better our learning trained models be robust to all this kind of noise. And even more, one thing I was thinking is that can we also really build a simulation engine for computational photography? So this is ASIC gene built by NVIDIA, which is very popular for robotic algorithm design, and people can play their robots in this simulation engine. I was wondering whether we have a similar simulation environment can let us design different cameras, even cameras that we never built in physics world, we cannot build before, but just testing the simulation environment to see how the camera works. I think that will be really impactful to the community. So that's one part, simulation. The other is that how the computational photography interact with hardwares. So Felix has given us a very nice introduction about all this kind of differential optics. I just won't mention more why it is important. But even more than that is that another thing for the combination between hardware and the computational photography is that I want to say is that the camera is not only for better selfies or just capture better images. Camera is actually widely used in many other applications. So this is one work by Katie Bowman in Caltech, and she did capture these first black hole images. And actually, under the hood, there's a lot of computational photography algorithms trying to recover the signals because the original signal is very sparse, and they use that to recover these very nice black hole images. And during that, it also need to analysis how this image is being captured using the BLBI image formation. And I think that our computational photography also can be contribute to many other areas, not only to our normal cell phones, but let's say medical images, many other applications also use cameras. And the third part, because Apple Vision Pro just announced a few days ago, and also think about how this can make impact to us. One first and obvious thing is that this may inspire us to build more better 3D capturing devices, like what Felix talked about, like this unintentional movement can help us capture some 3D geometry, and also the nerve, this nerve work, and then just capture multiple frames and combine them to recover the whole 3D geometry. And that's just one direction opportunities. But even more than that, one thing is that it will actually push us to make our cameras quite as good as our eyes. Because if you look at this kind of Apple Vision Pro, they use a technology called video see-through. Like basically, when you see some image outside, it's actually captured by cameras and redisplay on the screen inside the VR device. And this actually pushes us to see, can we really make our cameras can capture high dynamic range, vivid, high frame rate, high resolution videos as our eye can do. So that's a very good opportunities. And at last, it also can, similar to that direction, also push us trying to build as high resolution video processing pipeline as possible. Because normally when we say if you have 4K resolution, normal images, that looks fine. But if it's 4K resolution in 360, like a 360 format, 4K resolution you'll find is really blurry. You really need an 8K or 12K, 16K, really high resolution to make the image really looks like our eyes can actually see. And this actually provides us more challenges and opportunities to community. Another part is a lot of people talk about the AIGC. Nowadays, our networks are really powerful, generate a lot of video content, image content, and how that can impact our community. And one thing is that I was thinking, like, where's the boundary between editing and synthesis? So here's two images. One is through heavy editing, the other is really synthesis. I mean, you may say, okay, I can still tell which one's real, which one's fake. If I really look closely, saying this is a little bit fake, because if I really look closely, you can tell that. But because the algorithm includes large, how about like this? This is all synthetic basis and it's really real. If I don't put this citation here, you may just think this is real images. And then even that, this is one image generated by the Midjourney 5, which is really nice professional photos. So do we really need need this kind of editing algorithms in the future, or we can just use synthesis? I mean, this is an open question. I just put it here and for people to put discussion. And actually, this kind of discussion started a long time ago in 2001. Alyosha Akros and Bill Freeman, they built this kind of first kind of image synthesis, texture synthesis algorithms, and they find that when they try to apply this on texture synthesis of a text synthesis like this, you can generate some random text like this, looks real, but if you really look at a word, it doesn't make any sense. So synthesis is kind of in an interesting area for people to see whether which part is true, which part is synthesis, where the boundary is. And even more, if you look at all the cameras being developed in the recent years, this is all iPhone cameras in recent years. If you look at the cameras becomes bigger and bigger and powerful and better and better. That's the trend in the past 10 years. But if our processing algorithm is so powerful, it can synthesize some textures, do we really need such powerful lenses? Well, the lenses go through the revert way, becomes more and less powerful, and let the synthesis algorithm to do the job. I don't know. That's an open question here. One last part is that, as I mentioned, I also work in industrial, like all these cameras, industrial design, and I often find there's quite a lot of gaps when we say we develop all these fancy algorithms and trying to apply to reality. There's a lot of gaps when we try to really apply to our cell phones. One is that when we design an algorithm, we often report the image quality. But if you really talk to those engineers for cameras, they not only care about quality, but also about speed and power. And power is even more important than speed. And this is a trend of all the silicons power consumption goes up from years. And you can see that one important part is memory power, which is I like when I check all this image processing papers, very few people actually talk about the memory powers, because when you actually run an algorithm on device, memory actually costs a lot of power consumptions. And it's not only flops, but also how to reduce the memory. That's a very interesting topics. When we really see how all this nice computational photo algorithm runs on device. Another very interesting or challenging question is evaluation. So when we have developed algorithms, we normally use some PSNR to evaluate if the image is good or not. And this is a very nice demo by ISR again, when they show that the PSNR is not always the best metric. For example, this is by cubic interpolation, which is 21.95 dB. And this is ISR result, which is 21.15 dB, which is even lower than that. But definitely everyone may think that this image is much better than bicubic interpolation. And this just shows that PSNR is not the best one. And okay, you may argue, say, nowadays people not only use PSNR, but also in AirPits, IQQB, all this more better like perceptual metrics. But even that, it's not enough, because here's another example I would like to show. So here are 3 photos by 3 professional photographers. They're trying to tune these images to look better. And you can see that all these images, even all these professional photographers, they give us very different tuning. Some of this one is very bright, this is darker, and I think this is a kind of warmer colors, cooler colors. So each one has its own preferences. There's not even what is called a ground truth in this case. And how can we evaluate in this case? How can we evaluate when people have user has some different preferences?
there's open question about that. By the way, this image is from very famous Adobe 5K dataset. And if people work on that, you can just know that there's a lot of variation between expert tuning. And even more, when you try to talk to some photographers about the photo qualities, sometimes you can even understand what they're talking about. So when I first talking about, like say, denoising, when you have very nicely denoised, no-noise image like this, they will say, okay, this looks okay, but looks like an oil painting. And it takes me a while to understand what oil painting looks like is. It's like more like some really or like really use some oil painting to paint, have some brushes. Because this image is really painted by some brushes, not captured by cameras. And also like this sometimes some people may think this is a very nice HDR image, but if you show to this to photographer, they may say, oh, this looks too HDR, looks cartoon, like a cartoon world, not real world. So even trying to understand what's the best of what people's preferences, what people's feeling, it's not an easy task. And I think this is a lot of interesting research opportunities there as well. All right, that's the end of my talk. And this is all my collaborators. Without them, I cannot do this work. I mean, again, half of my talk is not by my work. It's also about the works in this community. But here's all the collaborators. Any questions?
So you mentioned that RGBR, right? So that's one thing is probably two camera right now more common, but right now very some emerging the automotive application, single camera sensor. So what's your opinion with RGBR in the mobile? What's your thinking about this RGBR single camera or single sensor solution for the mobile imaging? Do you see the trend or future?
I think it's a very interesting direction, and I saw there's quite a few demos on that. I think we just need to move, like, I mean, I think this is kind of a rising direction in the research community, and when there's enough like a good box being accumulated there, maybe like some industrial people will pay more attention to that. That's my general feeling. I think this is a very interesting future direction. It just needs a bit more time to accumulate.
By the way, for the EVS, actually, you said two camera solutions, and now actually it's also have a single sensor solution. So come to tomorrow EVS workshop.
Oh yeah, thank you. Yeah, you mean the Davis solution?
No, that's
okay.
Totally mobile.
Okay. Yes, please.
So what do you think about how the images are displayed will change the photography? I mean, you mentioned Vision Pro, that's a way to display the image. It's very different from like traditional display, but there are also like different resolutions of the display, the different sizes of the people view images on the phone, or people view images on a big screen like this, where you might care resolution more versus, you know, like care about the color and of the image more, or like Vision Pro, which is more like a 3D experience. And so what do you think about that?
Yeah, that's really good question. So let me just try to repeat. So basically the challenge here is that even the same image, when trying to view in the different devices, looks really different. So actually this image on this projectors, because the projector is relatively low quality, so the difference is not that significant. But if you come to my laptop, you'll see that it really looks quite much more different than on this projector. So it's, I think part of the reasons when people say we have these three images, people have different preferences. This could also come from device. Each when people looking at this image on their own devices, the device variation can be different. And also even the same device, like say in a very bright, like a bright sun condition, or even in a like very like a dark room, when you see it, it looks very different. So this even more challenging solution. People trying to say, can we do some environment light prediction to predict what this image may look like in certain environment. But again, this is a really challenging problem, but also that might be a more interesting research opportunity as well. Thank you. More questions? Yeah. Yep.
Our next keynote speaker is Sabine Satrank. Sabine Satrank is professor and director of the Image and Visual Representation Lab in the School of Computer and Communication Science at EPFL in Lausanne, Switzerland since 1999. Her main research areas are in computational photography and imaging, computer vision, and computer image quality and aesthetics. She received several awards for her research and teaching activities. She will organize the ICCP in July 2021 in Lausanne, Switzerland. Let's welcome Prof. Sabine.
Thank you very much. Aren't you guys freezing in here? I am freezing.
Yeah.
So thank you for the invitation. It's a pleasure to be here, and hopefully you did get it that I will be organizing the International Conference on Computational Photography 2024 edition in Lausanne. So I expect to see you all there. So what you're seeing here is a video that simulates a drone flying around a building. However, it is of course not a video, but it is a synthesized or rendered video from different images. And if you see at the bottom, it's a NERF scene. It's not a drone video, and we actually purchased it from this NERF marketplace. So NERF has been mentioned now twice by my previous speakers as something very interesting in the computational photography, and I would actually like to talk a little bit more about NERF. And the reason I'd like to talk a little bit more about NERF is because, to be absolutely honest, I was always an absolute fan of the planoptic function, which goes way back when. And then, of course, of the light fields and the light field cameras, which goes a little less back. And now we're going to talk about NERF, and I'm going to call this the neural grandchild of the planoptic function. So it's all kind of related, but it's a really interesting concept, and I want to talk a little bit more about NERF and then also present two works that we have done in the lab. So let me also acknowledge Yufan Ren and Dongjing Wang, who actually worked on the two research projects I will present and have also helped me put together this presentation. So what is NERF? NERF stands for Neural Radiance Fields, introduced by the seminal paper by Ben Mildenhall et al. And I already introduced planoptic function, and then the light field work, of course, made famous by Ren Munk in his Stanford thesis in about 15, 20 years ago, and then he exploited that in his startup Lytro. So we've always done a little bit of research into light fields, never that much, but it's really an intriguing concept. And now, as I said, we have NERF, who basically takes that concept into the neural network or the neural rendering field and has gotten to be much more accessible because it does not, to a certain point, take any hardware. So you can have new normal view synthesis using your mobile phone taking a few images. So for those of you not that familiar with NERF, and if you are, then I apologize to give you some really basic introduction, but I do want to give you a little bit of introduction before I actually start talking about what we have done in the lab. So what are neural radiance fields? Fields here stands in our framework for scenes, not images. And this basically radiance fields mean that the scene is represented by radiance or a radiant flux that is emitted at each point in the scene. And the term neural indicates that the radiance field is parameterized by a neural network. So let's start from the radiance field and see how it is used to reconstruct a scene from a collection of images. So we start by showing the connection between radiance fields and an image, the connection being volume rendering, and then move on to the term neural. As you all know, images are digitally represented as 2D collections of pixels. That's certainly nothing new. And in our framework, the translation of a scene to an image is called rendering. Now, rendering has many meanings in many fields of computer vision, computational photography, and computer graphics. In this case, it's basically a synthesis. Very simplified, it means to determine which color is assigned to each pixel. Given the principle of reversibility of light in computer graphics, we often model rendering as rays casting from its camera position outwards, so the ray casting, and observe how this ray interacts with the environment. Simplifying, we represent here the scene with triangle meshes. So you imagine the ray, in some distance, the ray hits the red triangle, and we determine the color of the pixel to be red. Now, again, it's an oversimplification of the situation. We do not take into account global illumination and any type of aliasing. So if the triangle is semi-transparent, we model its opacity. This parameter alpha is the opacity of the triangle and is a measure of the ratio of light that cannot pass through the triangle. Now, see that actually the pixel color is the weighted sum of the first and the second triangle. Here, the second one is not transparent. But what about 3? You know, the triangle is transparent. We have an additional decay because of the two triangles in front. And so on and so on. In conclusion, the color of a pixel whose radiance passes through n semi-transparent triangles can be written in this form. Here, alpha I Cj is the ith triangle's contribution, and the product accounts for the occlusion of the triangles in front of it. So rendering a radiance field is actually a continuous operation. In a radiance field, we have an infinite number of particles in the space, and each particle emits some light and may also absorb some light. The density of the particles is measured by volume density, and the amount of radiant flux it emits is measured by C. So volume density acts like a differential opacity, controlling how much radius is accumulated by a ray passing through X, Y, and Z. So to render an image from a radiance field, we need to resort to volume rendering. Recall the triangle rendering we described before. So now to discretize the space, we assume both the volume density and radiance are constant in a small range. Thus, we can derive opacity with volume density over a very short length of the ray. So alpha I is now a function of volume density and length as follows. We can thus render the radiance field with volume rendering. And this is nothing new. This actually goes back to research or publications that were done in 1995. So alpha, the volume density, is 1 minus the exponent of the alpha, the opacity is 1 minus the exponent of the volume density times the length, or the derivative of the length. So now what about neural? So radiance fields actually define a scene by defining a function mapping from a position x, y, z and viewing direction phi and theta to the volume density and the color. So we can actually represent this functional mapping using an artificial neural network. In other words, we use an MLP to parameterize this function. An MLP is a deep, fully connected neural network without any convolutional layers. So we sample many points for each pixel and render the pixel color with volume rendering and form a loss between the ground truth color and the rendered color, or the photometric loss. However, simply representing a scene as an MLP does not work. The reason is that neural networks do not work well when it comes to distinguishing small differences in the input. So here is a toy example using an MLP to represent the image. The MLP takes as input the XY coordinate that outputs the pixel color. As you can see, the MLP fails to actually capture all the detail. So what happens? The solution proposed in NERF is actually to use some positional encoding to inject high frequencies back into the system. And we do that with Fourier bases. As you can see, the learned image has much more high frequency. And so we get to this image we've just seen before, or i.e. the novel view synthesis that NERF actually proposes. Here is the flower scene that uses 34 images. And again, I really encourage you, if you have not already done so, to read the original paper. It gives you a much, much better overview than I did this. So what are the issues with this vanilla NERF I just presented? It actually has no restrictions on object material and geometry. Now, this, to a certain point, this is good, right? It can render almost all scenes relatively well because it doesn't make any assumptions. But it can also create a problem. And here I'll show you an example of what happens if you try to render a transparent object, like this glassware with NERF. So the research we have done, which I will present, is actually exactly how can we create visual plausible modeling using specific object materials. And the second is to utilize the learned prior of the network to improve the underlying geometry. So let's first talk about the object material. So vanilla NERF actually assumes that all objects follow kind of the Disney BRDF, i.e. they're basically smooth reflected surfaces. They do not take into account what happens if we have transparent objects or glinting surfaces. And these are the two actually object properties we're looking at. So a recent work called NEMTO, or Neural Environment Mapping for Novel View and Relighting Synthesis of Transparent Objects, jointly optimizes for object geometry and surface appearance for transparent objects. So NEMTO can synthesize novel views and relighted rendering of a transparent object given its 2D observed images. And here is an example. Now, the real contribution we actually are making is we're introducing a so-called ray bending network. And this one actually disentangles object geometry and light refraction. which in the vanilla NERF are basically kind of jointly optimized. So we take the learned geometry as a prior and model light refracted by mapping the incoming ray directions directly to the refracted ray direction of the object. So we at a certain point do not care what actually happens within the object, which is incoming and outgoing. So how does the system work? So we use the sight distance function, and I'll get back to that in a minute, or SDF, represented by a neural network, as the underlying geometry representation. After that, for each camera ray passing through the object, we query the SDF network for the surface normal, the viewing direction, surface normal n, viewing direction omega I, and then feed these two vectors together with the intersection position x into our ray bending network to obtain the outgoing direction omega t. Then knowing the outgoing the ray direction, we can use differential forward rendering to render the pixel colors, given, working with the color loss or photometric loss. And here's the results. So I'm just showing you the vanilla NERF, but even if compared to all the other state-of-the-art methods, we are actually doing quite better and resemble the ground truth much better. This is now based on synthetic results. So these are synthesized views, but we can also actually do it on real images. And this is real world capture data from the TLG dataset, as through the Looking Glass dataset that was presented here about 3 years ago. Not showing you is that we've actually now tried those with mobile images, and it actually works relatively well. So this is now an extension where we really specifically look for different kind of material properties. How our network actually works when we have multiple objects that I cannot tell you because we haven't done this yet. And this is, of course, an extension to think about because real life scenes have different kind of objects in the scene and not a single one. So the second paper that I would like to present to you is how we actually use learned priors of the network to improve the underlying geometry. So with, this is kind of like the A and O of much of the machine learning, communities research is kind of like, okay, well, when we learn a prior, how in the world can we use it? And so this is what I want to show you. Basically, that if you exploit these learned priors, you can actually reconstruct a scene with very few images. Recall we used 34 for the flower scene. Here, I'm actually presenting some work that we use as few at 3 images to reconstruct the scene. So we know that NERF is very flexible and can really nicely reproduce visual realistic scenes, but we do know it's hard to extract a mesh from the scene, from the learned scene. And so this is where the solution came in to actually represent the scene as a signed distance function. And that is actually done by the work of Wang et al., which is called sparse news, learning neural implicit surfaces by volume rendering for multi-view reconstruction. So different from the volume density NERF, they use the signed distance function as surface representation. So the signed distance function measures the distance from the point to its nearest surface. So this representation is much more constrained than the NERF representation or the density field, and it actually can achieve better surface reconstructions. But on the other hand, we still want to use the volume rendering. Right? We don't want to give that one up to have all the advantages of the NERF architecture. So the solution provided in the sparse newspaper is to convert the SDF values into rendering weights for volume rendering. So we are interested in this line of work But we actually kind of wanted to exploit exactly what I said before. What happens if we use much fewer images than in sparse nearest? And again, recall before, the flower images with 34 images, we want to do it as few with the label S3. So the generalizable neural reconstruction actually starts with n source views. And can be any number, hopefully few. And here specifically, sparse news extract feature maps and creates a feature volume using epipolar geometry. The global feature volume is regularized with a 3D convolutional neural network for a large receptive field. Then, from the global feature volume, they interpolate features and decode them to signed distance functions, values. But you can imagine that actually the resolution of this is limited because it actually depends on the voxel resolution. So as a consequence, even their method actually still lacks quite a bit of detail in the reconstruction surface. So we propose a different pipeline just to retain those high detail information. And the intuition is as follows. So recall that in volume rendering, we need to break the camera rays into little pieces, so to have constant volume density. So for each slice, we use the interpolated SDF features. Because the problem by the previous work cannot be constructed by detail was actually in the volume resolution. So the idea is to add a new branch that goes from image feature extracted by a neural network directly to the rendering. So more specifically, we use a view transformer to aggregate multi-view features and then use a ray transformer to calculate SDF values of the points. Here we determine sine radiance distance sine ray distance function, since our distance function is view dependent. So our distance function defines the distance to the closest surface but along a given camera ray and not just independent of the camera ray. So we combine the global shape height from the global feature volume and projection features. And here we can see the results. Pick this up a little bit if I can. So this is on the left, we see the baseline, and then we see our swirl recount on the right, 4 different scenes. And I hope you can see that the reconstruction of the details. It's still somewhat noisy, but it does have higher depth. So the result is a much more detailed surface reconstruction compared to the baseline. And of course, similar to NERF, we can also render novel views. So as a conclusion, I truly believe, as also my 2 previous speakers said, that NERF, or this novel view synthesis, is an extremely exciting area in mobile imaging, because you can get away with a few images and you can now reconstruct the scene and not just reconstruct the image, which we have done forever and ever and ever and ever. But now we can actually reconstruct the scene. However, there is still quite a bit of work to do that. So, extending it to material, extending it to large scene, extending it to large scene with multiple objects and multiple materials. What happens if you have noisy camera input, etc., etc., etc. There's actually a NERF workshop parallel to ours, which many of these things will be addressed. And I think there's going to be a lot of interesting work coming down the pipeline. So I just showed you 2 contributions that we've done, but many, many more to be will come down the pipeline, and of course by many, many different researchers. So here are the 2 QR codes for the papers. The Valrecon paper is actually joint work with ETH Zurich and is a poster at Thursday morning. Then just to considering I have a captive audience, I'm going to make some advertising of some of our different work. So we have also a saliency prediction. As you know, I am very well known for our saliency work. So of course we still use, have some interesting work on temporal information, how to help in the salience prediction. Then we have some that will be presented on Tuesday afternoon. Then we have some spatial temporal self-supervised learning for point clouds. Oops, that was a little quick. And that will be presented in Tuesday afternoon, and some really interesting work on real-time dynamic texture synthesis using neural cellular automata, which basically achieves speed ups of 2 to 4 orders of magnitude compared to the state of the art, which also will be presented on Thursday afternoon. And then we get back to the QR codes, and thank you for your attention, which of course means I did not even use 20 minutes of my 15 minutes, but I think you probably won't complain because there's many interesting things to go listen to in this conference. Thank you.
We still have some time for quick questions. Any questions from audience?
Very nice talk. I have one question. So my view of nerve is actually also kind of a compression algorithm in the sense that like from this like a 5A function x, y, z to field direction mapping, you can just store everything into a very gigantic matrix, and this kind of MLP actually trying to compress it. What I'm trying to ask is that, do you think that like the MLP is sufficient to compress that, or like saying also there's some work trying to add some prior to it? Does that actually help to further reduce the size of nerve? Oh, yeah.
If you want to further reduce the size of the nerve, you probably do this, the quality will suffer, right? I mean, all the Pi kind of information is actually to get rid of the, some of the artifacts MLP actually introduces. So I think, in my opinion, right now, I'm not saying somebody will come up with a brilliant idea in 3 years and then I'm talking about something else. It's kind of a trade-off, right? So the more you compress it, and there are models now that you can put into a mobile phone, the quality is just not there yet, right? So you need to make all these assumptions, all these priors, and you need to put those in, but that actually usually makes your model more complicated than simpler. So yes, I think that there's still a trade-off between quality and complexity.
So in another word, can I understand in this way that if we maintain the same quality, nerve may already reach kind of its limit to how much we can compress at this moment?
I would say so, yes.
Yeah. Thank you. Thank you.
But it's still cool.
Yes, yes, I agree.
Okay, thank you so much for
Thank you.
presentation. This is all repeated.
Yeah, thank you very much.
Okay, now we have covered for keynote speaker. I would like to thank you for our keynote speaker and audience for joining us today. We will end our workshop today. Thank you for everyone. Thank you.